Here we see
Check one, two. 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 Check.
What?
Again, standing, walking around, eating a bit. Yeah.
Hello, hello.
Yeah, yeah. Yeah, I just saw now the first presentation. Recognize the name.
Data
Yeah. Maybe. Did you do a more practice session? You didn't? The red canvas is Ah, okay, I thought that. No, no. Yeah, but there's other ones at the demo. Oh, yeah, yeah, yeah. But no, yeah, but I was thinking the demo session on Monday. Yeah.
Exactly. So thing is, the not here sure.
Yeah. Oh, yeah. Oh, yeah, he was late because of the interview.
I mean, he's not.
Yeah.
He's not late.
Oh.
Sounds good. Okay, sounds good.
All right, good morning, everyone. You are the few, the lucky and the proud who have made it to this, the most important session of UIST, Data Dreamers, Math, Stats, and Viz. So I'm Jeff Bigham, I'm from Carnegie Mellon University and Apple, and we have a really fantastic set of talks for you in this early morning session on the last day of UIST. I like to say, people are really excited right now about machine learning, but what is the human side of machine learning if not math, stats, and Viz? And so I think it's really important, really vital session of really important work, and we all get to hear about that together. So first off, we have Zed Wu from University of Pennsylvania, who'll be telling us about a really interesting system for labeling and working with math notation. Yeah.
Yep. All right, good morning, everyone. My name is Zed. I'm a master's student at the University of Pennsylvania, working with PenHCI. Today, I'm here to talk to you about Formula Formatting Language, or FFL, a markup language and live runtime for styling and labeling math formulas. Let's start with why this is useful. I came across this formula when I was reading a textbook the other day. It's a relatively simple compound interest formula, but I could not figure out what some of the symbols meant. For example, what are the big and small n's? Why does r hat need to be divided? So I went back to the text to read the definition of each symbol, but this being on a full page of text, it was not easy to navigate between the formula and the right part of the text for me. What I wish I had was some sort of visual cues like this. With each symbol colored in both formula and the text to direct my attention, I can clearly see F is the principal amount, R is the annualized interest rate divided between n periods a year. Similar to syntax highlighting code, it makes it easier to figure out what each symbol means. Augmentations like this are common among web articles and tutorials, but they're also seen in textbooks, research papers, explainer videos, and contents of many sorts to dissect dense technical information. However, even augmentations relatively simple like this are often messy to do, which might partly explain why they're not more ubiquitous. In fact, to do this in LaTeX requires an unruly amount of text colors and oftentimes necessary curly braces. Not to mention, to synchronize repeated cross-cutting changes, you either need to change each occurrence individually or have the foresight to declare them as macros in advance. So we set out to design a language better suited for the needs of math augmentation, with which we want to make it easy to style and label formulas, allow repeating augmentations for repeated symbols, have easy-to-read syntax, integrate with common web authoring environments, and provide some live feedback. So we designed formula formatting language, abbreviated here as FFL, which is the main contribution for our paper. You'll notice that FFL looks a lot like CSS, which is one of our main inspirations for how we achieve some of our goals. To do the same augmentation like this as before in FFL, you just write down what elements you want to style and how to style them as a style sheet, and voila, you got the same result without the insanity of nested braces macros. This is much easier to read than the LaTeX we saw earlier. If you're not happy with the color of a certain element, all you need to do is change one line. No more searching through the entire document to verify every single instance of the same color. Let's talk a bit more about the language itself. As we've already seen in some examples, like CSS, FFL style rules consist of some selector followed by a block of properties. The most basic type of selector is a literal selector of some LaTeX math, just as you would write in the original markup. As seen here, surrounded by a pair of dollar signs, and selects anything matching its content n. And since one of the core features of FFL is the ability to reuse changes, we also support glob-like wildcard syntax to match any single or sequence of tokens. Here, the selector selects any fraction with any numerator and a single token-long denominator. Of course, this is just a taste of what FFL can do. FFL already includes many more selectors, such as the nth instance selector and some built-in classes, as well as common augmentations, some of which are directly enabled by CSS, such as color, font weight, text decoration, as well as FFL-specific ones, such as label and selection-wise background color. You can do all of this with our runtime, which can be integrated into live web authoring environments, such as the demo we host on the web. Here's how it works behind the scenes. When FFL renders a formula, it first tokenizes the formula, then it parses the FFL style specifications, tokenizes the selector the same way as the formula, and generates relevant CSS from the specification. Then it finds the matches of selectors, inserts special marker tokens to delineate the ranges of styles. With the inserted tokens, we then continue to render the formula into HTML, which is then marked with the appropriate CSS class names, matching the CSS generated earlier. Finally, we apply the styles to the formula by attaching the CSS to the rendered HTML. Here, we also do some additional processing to handle non-CSS properties, such as labels. The final combined result is what is rendered by the browser. To test how useful FFL is, we conducted a user study with 33 participants, each completing a set of tasks, some with FFL and others with a LaTeX baseline. Here's what we found. In editing tasks with more complex augmentations, we saw a significant speed-up of around 1 minute using FFL compared to a LaTeX baseline. Namely, the two editing tasks shown on screen, which were completed on average 26% and 19% faster, respectively. Otherwise, in simpler augmentation tasks, we found no statistically significant difference compared to LaTeX. Participants also found it easier to complete tasks with FFL compared to LaTeX baseline, with more blue or bigger segments on the right indicating strong agreement with the statement. In particular, FFL participants found FL to be, quote, easier to read through because styling code is separate, and liked not worrying about layers and layers of braces. FFL eliminates a whole class of common errors with braces such as, in latex, such as a missing closing brace, as seen here in the figure written by one participant. It is also found to have the ability to easily make changes across multiple symbols, fewer hard mental operations, and useful live feedback. We were also given a few feedbacks in the study on how to improve FFL in areas such as learning syntax, discovery of constructs, error recovery, as well as more features to be desired. Other than the more obvious improvements, here are some more exciting ideas on how to continue expanding on FFL. For example, despite many benefits of using markup language, there is still demand for direct augmentation tools. FFL could serve as a springboard for a tool that supports best of both worlds. With this, it might also require additional support for scoping, in other words, styling the same symbols differently in different parts of the text. These are just some examples of what you can do with FFL. For more information on the project, which would not be possible without a wonderful team, some of whom are here today, you can reach out to us after the session or check us out at our website at penhci.github.io/FFL, which also links to our interactive web demo. Thanks for having me, and let's open the floor for questions.
Both fantastic work, and your presentation was really, really excellent. I really enjoyed it. I would love to, I didn't introduce myself. I'm Arvind, MIT CSAIL. I'd be really curious to hear more about how you're thinking about separating concerns. I noticed in FFL that you're able to do augmentations as well as just styling. And so I'm curious, how do you think about what should go in the LaTeX versus FFL?
I guess we model FL after CSS in many ways, and we mixed augmentations and stylings together. And to me, LaTeX should be the main document markup, which is the, I guess, kind of semantic content that you're trying to present, and everything else should fall, I guess, besides that. But I understand that it can be, I guess, when it comes to labels, it can be a little bit ambiguous between the two, and we've just chosen to put it inside of FFL since it's a common augmentation.
Great, thanks a lot. Very excited to use it.
Thank you.
Hello. Ooh, I'm on this side. Michel Baudouin-Lafont, Université Paris-Saclay. Great work. This kind of thing that we all want to have in Overleaf or whatever. So a question I have is, have you thought about how to extend this to support some form of interactivity with the formula or between the formula and the text?
Yeah. So there are actually thoughts about that, but we don't yet have a concrete design for it. I think some of our colleagues here today are going to talk about interactivity here as well, so maybe that will be of some inspiration there as well.
Yeah. And would you also consider doing something with evaluation of those formulas so you can derive plots and so go beyond just styling a formula to?
Yeah, so we do think that would be useful because it is a common way that math formulas get augmented. Again, the design isn't very clear at this moment, but it is certainly an idea on how to expand FL.
Okay, thank you.
Thank you.
I've got one last question. So this is really cool. I was wondering if you could kind of push in, maybe actually related to Arvind's question, a little bit more about how you think about semantics versus presentation. And so one reason I ask is some of the, especially in the initial examples you gave, were very much about colors, adding colors to things. And I wonder about that from both the separation of semantics and presentation layers, but also from like accessibility. Have you thought about like what actually goes in this kind of markup to do semantics? Because some of the things even on this slide, right, the labels, right, that's kind of semantics. And they're in kind of the presentation layer possibly. Could you kind of talk about that?
Yeah, so when it comes to labels, I think it's more, a lot of times it is used to enhance I guess, the comprehensibility of the formula, and the content is often, often included in the surrounding text as well. Same thing with colors. It is often used to connect a formula to the surrounding text. But in terms of, and sorry, can you repeat the last part of the question again?
I already forgot it. Accessibility was
Yeah.
part of that, yeah.
Yeah, so I guess accessibility, this is, with colors, there might be a concern there, which is why more sorts of interactions would make this helpful. And also this being a language, I think there can be ways to do accessibility checks automatically. I think that might be a direction that could be interesting to head into as well.
Great, well, thank you. Let's thank the speaker again. All right, while Damien gets set up, I guess I'll introduce your talk. So one of the things I really like about this paper, which I thought is just really, really cool, is, I used to joke that part of presenting statistical results in Chi papers is kind of keeping up with whatever the trend of the current way and expectations of the community about presenting statistical results. And so I really like this paper because it's actually about kind of translating between those various different ways. And so maybe we don't have to worry about like the particular way we're reporting our significance testing, but maybe we can actually get down into the actual science using the system that Damien is going to present. So take it away.
All right. Thanks, Jeff. That's actually very true, and I'm going to talk about that actually. I'm Damien Masson. I'm a postdoctoral fellow at the University of Toronto, and this is work actually I have done as part of my PhD thesis with my advisors Sylvain Malacria, Jerry Casier, and Daniel Vogel. So I know Halloween was yesterday, but I actually have a scary photo for you, so be prepared. So this photo is scary to me, but not because of the value of p. In fact, it could show a p-value of 0.0001. I would be just as scared. No, the photo is scary to me because the only thing reported is a p-value. And this p-value gives me very little information. So with just the p-value, I do not know the size of the effect. And frankly, the value of p could be 0.01 or 0.05. It would not mean much to me. And I'm not alone in being scared by reports that contain only p-value. In fact, many recommended alternatives. So, for example, it is common to report additional values, such as Cohen's d, to convey the size of the effect. It has also been suggested to replace p-values by confidence intervals. And it is recommended to report these confidence intervals graphically. And many more alternative solutions have been proposed, such as plots showing plausible values through an animation. All these solutions are great, but they have to be adopted by authors. Otherwise, readers are stuck with the statistical presentation in the paper. So the question is then, what can we do for published papers that do not follow these statistical reports, these statistical reporting practices? And in this work, we answer this question by showing that in many cases, these statistical values can be recovered, and we can also provide the readers with a tool to change the statistical presentation and choose the one that they prefer. And so to do that, we first analyzed 40 years of Chi papers to know what and how statistics are reported. We used the Python script to automatically count dimensions of statistical tests and statistical values. And it also counted the number of decimals used to report these values. And we found that t-tests were the most common statistical tests. And looking at the reported values, we found that the majority of papers reported only p-values, but they also fairly commonly reported means and standard deviation as well. We then derived equations to convert between statistical values. So we focused on t-tests because we just saw that they were the most common, and also because with t-test there is a relationship between the confidence interval and the p-value. So all the details are in the paper, but for example, given just the means and p-value, we can calculate the confidence interval on mean difference. Given the confidence interval on mean difference, we can calculate the p-value. Given the mean and standard deviation, we can calculate the confidence interval, although this only works for between subject study designs. And given a confidence interval at any level, we can change the confidence level. And given a p-value, we can calculate effect sizes such as Cohen's d. So of course, this is just a subset of all the possible conversions. These conversions work both ways and can be combined. So for example, we could convert Cohen's d into a p-value and then use that p-value and means to get the confidence interval. All right, so these conversions work in theory, but what if values are rounded in the paper? Or what if the p-values are corrected using bond theory? Or what if the confidence intervals are calculated using a bootstrapping method? All these are common in research papers. So that's why we conducted multiple Monte Carlo experiments to simulate reports in scientific papers. So we varied the study design, the sample size, and the type of conversion. And we also specifically tested different rounding precisions because values in papers are usually rounded. And we found that overall, the equations were accurate to translate statistical reports if values were reported with at least 2 decimals. So for example, conversions to confidence intervals were a bit off with 1 decimal, but very close to 95% with 2 decimals. And even bootstrapped confidence intervals can be converted to p-values with reasonable accuracy. Finally, we developed StatSlater. It's a PDF viewer that allows to interactively translate the statistical reporting styles in existing documents. So after a text selection, we use ChatGPT to extract in the text the statistical values. And then the system generates a table with all the values it could calculate from the information in the document. So users can review how each value was obtained. So values in green were obtained from the text in the paper, and values in blue were automatically calculated. Again, users can verify how they were calculated by hovering over them. And then readers can customize the presentation of the statistical report. Here, for example, the system was able to calculate the confidence intervals even though they were not reported in the paper. And the presentation can be changed, so for example, to show the values graphically and through animated charts. So this allows readers to interpret statistics in a familiar style, compare the statistical reports from different papers by making them share the same presentation style. And because the system is able to calculate different values, it can also help detect errors and inconsistencies in existing papers. So for example, here, the p-value reported in the paper does not match with the t-score that was reported. So that's why it's shown in red. But other inconsistencies can also be detected. For example, if the confidence interval is not consistent with the p-value. So to summarize, we answered the question of what can be done for published papers that do not follow the statistical reporting practices I showed in the beginning by first analyzing the values and reporting practices in CHI papers. We then derived equations that can take these values and convert them to other values, such as confidence intervals. And we validated that these equations were accurate even under reporting practices common in research papers, such as rounding to a few decimals. In doing so, we contribute a JavaScript library to translate between statistical values, and StatSlater, a PDF viewer to help readers change the statistical reports in existing documents. So before I finish, I want to point out that all the data and source codes are accessible online. We also released the StatSlater library that can be imported into any JavaScript project to translate statistical values. And we also made a simple interface for the library. It is accessible online if you ever need to quickly convert a p-value into a confidence interval, or calculate effect sizes, or visualize the data, the statistic. Thank you.
While you're thinking of your question, is that a question? Are you sneaking away? Okay.
Hi, great talk. I wonder, you said you use some kind of language model to extract the stats from the PDF. Have you noticed any errors cropping up that way, and how do you make sure that it doesn't kind of fail at the last step because the extraction went wrong?
Yeah, that's a good question. So yes, we use ChatGPT because like in our test, that's what worked the best to extract the statistical values because they can be reported in very weird ways. And so it is, so ChatGPT is doing very well, like in our test. But it is possible it makes mistakes, of course. And so what we did in the tool is like we have this, those interactions to help users verify that the extraction is correct. So like if they hover over a value, they're supposed to see like the corresponding one in the document, so they can make sure that like it's properly extracted. And yeah, they can check that way, but like it's correct. And we also have like a more manual mode. So if they don't trust the ChatGPT model, they can just use input the values themselves. It's not that much work. Yeah.
Great, thank you.
Hello, I'm Takeru Igarashi from Tokyo. So this is general question. So yeah, I agree that every paper does slightly different way of reporting and that's problematic. So my question is there any rule book or guideline official from CHI or UIST about this or not? And if not, I think there should be. What do you think?
I completely agree with you. So I guess the guideline would be, I mean, there is none for CHI that I know of. There is the APA, but like we cannot follow in CHI. Like I can't remember what it stands for, but like it's like a guideline on like how to report statistics. And so usually they say that like, oh, you should report like p-values, confidence interval, or like any kind of effect sizes. And what's interesting with this work is because we look exactly at what information you need to convert the presentation, I can tell you exactly what is the bare minimum information to report in the paper. So I think this work could inform how to report.
Yeah, you should negotiate with organizer of CHI to integrate this into PCS to be consistent. That's serious. Thank you.
Thank you.
This is super cool work. Thank you so much for sharing. I'm Justin from UC Berkeley. One thing I was curious about is how much of it is reliant on like a parametric test, like being a t-test, and how much of it could extend to like a wide variety of different tests?
Yep, that's a very good question. So we focused on t-tests mostly because they were the most common, but it's true, like they make it easier because like a t-test, we know that like the data, or at least like the, what do you call that? I mean, the data is going to follow a normal distribution, otherwise you shouldn't use that t-test. And so because of that, we have more information to calculate our confidence interval. If you had something, so non-parametric, so Wilcoxon, for example, you have to know the distribution somehow, and well, because it's non-parametric, you're not supposed to know. So what I can imagine is either like the user provides that information, because sometimes, you know, like our time, we know usually it's going to follow log distribution, yeah, I think. So we could do something like this, but yeah, it's clearly not as easy as a parametric test. Yeah.
Cool, thank you.
Hey, Bjorn Hartman, UC Berkeley. You solved the harder inverse problem, and I'm wondering if you could now, from what you've done, solve the easier forwards problem in helping authors make sure they add enough information for later tool augmentation in a whole number of cases. So is there an authoring tool hiding in your reverse engineering tool?
Yeah, that's another great question. So it's something we talk a little bit in the discussion. I do think it could serve as an authoring tool because, like, as I said, like, so it could show you like the values that are calculable from what you reported in your document. So already it could tell you, okay, there is not enough information to change the presentation. Maybe you should include that value. But it can also detect inconsistencies, and so like that happens. Like, I mean, we all we author papers all the time, so we know that like it happens that like, oh, you report the t-score, but like the p-value you change it because I don't know, something happened, and so that can detect those inconsistencies. So I think really there is an opportunity for an authoring tool. So I think it's a great question, and great for future work.
All right, these two questions, and then we'll be.
Hi, I'm Eunice John from UCLA. I'm curious about how you think end users will be able to understand the metrics that you report, especially given many end users might not even understand what t-tests, you know, to use or to report.
Yeah, that's a good point. So So I want, like with this work, we kind of wanted to make like a, or you choose the presentation that you prefer, but it still assumes that you know at least one of the presentations that we offer. I think it could be very interesting to look into maybe metaphors or like ways to understand statistics that are not like you have to know how like to interpret the p-value or a confidence interval. So it's not there yet. Right now, we're just focused on more like, we take what is reported in the literature, what are the best practices, and we offer those to the readers, so they have to know a little bit,
Hey, Brandel Zajanuk from Apple. This is really exciting work for having sort of a multivariate view of what data is in a paper. ACM recently announced, maybe last week, that this will be the last year of paper print publication of papers. Are there any sort of practical implications that you would like to sort of encourage to carry forward in a world where papers are no longer paper and the sort of the material characteristics of it can be slightly more flexible for the purposes of sort of these different views?
So let me rephrase the question. I'm not sure I got all of it. So you're saying like we're moving away from printed papers, so can we use that like digital format? Yeah, I think it's a great point. So like one of the things I showed is like there are those animated plots, and they've been shown to be more understandable for people, like because it's an animation that shows like possible means that you could have gotten if you had rerun the study, and I think those like are they're called a hypothetical outcome plot. And I think typically those like they can only be on a digital format because they're an animation, and typically they're like, to come back to the question before, they're easier to understand for people that do not know p-values. So I think there are great opportunities for that.
All right, let's thank our speaker again. All right, so I am slightly failing as session chair here. We're a little bit behind, but I know how excited everyone is about significance testing. And so I wanted to let the... we have a fantastic next speaker. And I think the connection, which I drew between the last paper and this one, is that both of them are trying to reinterpret and reimagine kind of existing material. And so in this case, we're going to look at static math diagrams and convert and augment them with augmented reality exploration to them. So, Millie.
Thank you. So my name is Millie, and I'm from Aarhus University, Denmark, and I would like to present augmented math, authoring AR-based explorable explanation by augmenting static math textbooks. So this work has been done in collaboration with colleagues from University of Calgary. So explorable explanations is this great vision by Britt Victor about going from static explanations to these explorable explanations and go from consuming text to really be active readers and explore the text. And he has these really great visions about changing values and see the effect in the document and explore these graphs, how they change compared to values. And this vision has been quite adapted in particular in the STEM education and in particular in math. And there is a lot of great resources online. However, using this in the education, it's very time consuming to find the relevant material, and it's very disconnected from the other teaching materials, which is still regular math textbooks in most cases. So we have seen a lot of author related work on how we can make better documents in the first place. For example, yesterday we saw the living papers, and this is definitely the future to create interactive documents. However, it still requires right now to recreate the teaching material that you have in the book to make them interactive, and it requires technical skills to create these custom explorable explanations. So in this work we ask, how can we create explorable explanations directly from our existing math textbooks? So we have built this proof of concept prototype where we extract the content from static math, physical or digital math textbooks, and make them into explorable explanations. So to do this, we have a four-step authoring process. So the first is to extract the content from the physical book. So we use OCR to extract the text or the equations, and then we use a custom computer vision algorithm to extract the graphs and figures from the static math textbooks. Then the author binds the equations and the graphs to make this connection and make it possible to then augment the graph and present it in a way that you can now begin to explore what will happen if you begin to change the values. So in this example, we can see directly on top of a static math textbook what happens if we change the 2 in the sine curve. It will change the curve completely. Finally, we don't just have this one directional binding where we can change the equation, but we also can change the figures directly. So we have this bidirectional binding between the two, and then we see the effect in the graph as well. So augmented math, we both have an AI application working on a phone or on a tablet, and we have a web interface where you could put in PDF documents and augment them directly. So augmented math supports 5 different augmentation features. These are based on an analysis of existing explorable explanations online. So we support dynamic values, interactive figures, relationship highlights, concrete example, and step-by-step hints. We have already seen the example for the interactive figure in the presentation, so let's just look briefly at the 2 other examples. So the relationship highlight, we now bind 2 graphs to the relevant equations, and then when we change, for example, the x value in one of them, we see the effect in both of the graphs. So we can now not only understand one graph, we can understand 2 of them, or coordinate systems in this case. So we get this relationship between different aspects of the book. And another example is getting a concrete example for something abstract. So for example, this summation can be pretty hard for not that mathy people. So just getting a really concrete example, what does this means with actual values? So to evaluate the system, we did a technical evaluation and 2 user studies. And in our technical evaluation, we analyzed 140 pages from 14 different textbooks, and we found that in particular equations and graphs work pretty well. We can maybe use a bit more work on detecting geometry from the books, but we have a lot of work to do in this. So for example, the equations, it's usually an extra space or an extra new line, which is not that bad. And in graphs, it's often the decoration lines, which makes it a bit harder. But I think there is a lot of work to improve this by either that the author inputs a bit more information to correct the errors, or obviously improving on the algorithms to extract the information in the first place. So from our user study, we evaluated on 11 users trying these explorable explanations in static math textbooks, and they particularly liked the interactive figures and the relationship highlights. And we did an expert interviews with 5 math teachers and instructors, and they really liked that they could use the existing material and then engage their students through this interaction with the textbooks and this very reduced authoring effort for them. So this is, we shouldn't stop with math, but I think we should incorporate the 2 last talks we just saw into this. That should be possible. But I think we should look at this in general for printed material. In physics education, it would be nice if we could extract physics simulations directly from the book and then begin to manipulate the figures and see what effect it has. We could imagine that we don't just augment with visual content, but also augment it with sound, something like that in, for example, music education. Or we could imagine not only augment with 2D content, but also extract the content and make it into 3D content to get more information than we have in the current textbooks. So, in summary, we present augmented math. This machine learning-based approach to author explorable explanations by augmenting static math textbooks. We present this set of 5 augmentation features, and we present key findings from our user study. So thank you very much, and we are happy to take questions.
Hi, James Egan from Institut Polytechnique de Paris. This was really nice work. One of the questions that I had is how much do these augmentations, in your context, it's focused on physical textbooks with sort of AR headsets, but you showed in the presentation working with a live interface.
Yeah.
And so how much do these augmentations depend on that sort of context, or could they translate to an arbitrary window with, say, a PDF in it?
Can you one more time?
So could these techniques that you're applying,
Yeah.
in this case, to paper detected through a camera in an AR system,
yeah.
could that apply to just recognizing images on the computer screen and, say, a standard PDF
Yeah, of
viewer?
course. We have a web version of the same thing, just using a regular PDF in there, and you can do the exact same things right now. I think actually the web version is easier to interact with compared to the iPad holding it on top of a regular paper, so it's definitely need for improvement in just the interaction with an actual AR interface. And if you move to head-mounted displays as well, how do you then interact with the content directly? I think there's a lot of future work in that.
I think there's some really, really great ideas for how you could just take arbitrary fixed interfaces and completely extend them without having to tap into the code.
Yeah. Thank you.
Thank you.
Hello, Michel Baudouin-Lafont, Université Paris-Saclay. Great work. I was wondering what was just follow up, in fact, what was the motivation and you think the advantage of doing this through an AR interface rather than, snapping a picture and being able to work on the tablet?
Yeah, I think, so the first motivation was that you really merge the physical paper and the AR to see it directly, but I agree that probably the interaction would be easier snapping a picture of the page, but I think more work is definitely needed to explore which types of interaction, and also, again, if you move to different AR headsets and so on, then how would it work? Then maybe it would make more sense to have the augmentation directly on top of the page, where if you have some handheld AR, I think probably snapping a picture and so on would,
Yeah. And I have a different question, which is, since doing automatic recognition of the formulas and the diagrams is challenging, is there a way to sort of start from what has been recognized and then fix it if it's incorrect?
So in the current
thing?
prototype there is not, but I think definitely I think our users, for example, said in our step-by-step hints there were way too many hints. And the idea is that the teachers should author this for the students, so they should decide which things should be interactive in the textbook and decide in which level of detail the different interactions should be. So I think definitely future work would be to make more authoring process for the teacher to correct or to adapt to what the needs are for their students.
Thank you.
Thank you.
2 more questions.
Hello, I'm Josh Horowitz from University of Washington, and thank you for presenting this really magical work. I was especially curious when I saw the example of dragging the corners of a right angle triangle, because to be able to interact with a diagram like that, the system must have some understanding of the constraints inside of the diagram. And I immediately start thinking, well, to do that in general, for any sort of system, to do that with the lens diagram, say, it seems like downright intractable. There's so many things that could happen. But do you feel like there's automatic approaches that do make that sort of thing tractable, or are there other kind of authoring experiences around that would makes that work in a broad variety of diagrams?
I'm not quite sure.
I'm sorry. Well, maybe it's easier than I think it is, but just the fact that when you drag around parts of the triangle, say, it needs to know that one corner is a right angle, say. So there must be some intelligence in there that tells it, here's what a right angle is, here's what two sides being the same is, those sort of constraints for manipulating a diagram.
Yeah, that's true. I think in the current system we do detect that a bit, but I'm actually not quite sure. I don't remember exactly how it works in the current system, but we can discuss that further afterwards.
Sounds great. Thank you.
Thank you.
Hi, Sang-Ho Seo from University of Toronto. Thank you for a great talk. I really enjoyed it. So my question is, have you guys considered exploring, changing, representing it in different representation that would be more concrete than mathematical, which is representations which are more abstract representations, right? So if that's the case, if you guys have considered that kind of direction, I'm wondering what kind of possible representations could you guys can play around with it, right? Because oftentimes when you're presenting these mathematical concepts, you might want to use analogy or stories, and if you know Brilliant, they kind of do all sorts of manipulation with more concrete representation. So
I think in a lot of the content we analyzed from online, we also saw a lot using sort of not concrete examples in terms of value, but more like putting it to, for example, matrices into an image and see how that changes the image colors and so on. So we did definitely discuss how we could sort of bring in more, lifelike examples to change the representation of what the math is and what it means. But yeah, more work is needed to support that.
Yeah,
thank you.
Awesome. Well, let's thank Millie again. Thank you. All right. So as our next speaker sets up, so you really want to stay for this. Welcome everybody who didn't make it to 9 a.m. Also, you should definitely stay for this one. This in this session I think is the most like, oh wow, this is UIST, and it's Viz, it's math, it's engineering, and it's also fabrication. And so connecting all of these things through weaving, which is just remarkably awesome. And so Samantha is going to tell us about that.
Hi everyone, I'm Samantha, and today I'm going to be presenting my work, Spear Loom, an open source loom kit for interdisciplinary engagement. So bear with me, I know we're in a math session, but I'm going to talk about weaving for a little bit. So weaving is shaped not only by art, but also by mathematics and engineering. So the history of weaving holds many engineering innovations, including the innovation of punch card programming with the first jacquard looms. And not only have engineering advancements come from weaving, but mathematical theory in geometry, set theory, and linear algebra has been developed around the structure of woven cloth. So in fact, a typical weaving pattern, like the one shown on screen, can be represented as a series of binary matrices. So the black and white matrices show how the weaver is going to set up their loom and how they're going to weave on their loom to create the pattern that they're going to make in their cloth, which is shown in the orange and white matrix. And so these matrices can actually be rearranged to create an equation for a cloth's pattern as a multiplication of the loom setup with the row by row weaving instructions for that pattern. And so given this interdisciplinary nature of weaving, we wanted to take advantage of these connections to bring interdisciplinary learning into the classroom. We decided to teach a post-secondary class at Carnegie Mellon University where students would build and weave on their looms in order to learn the basics of weaving, linear algebra, and engineering all together. In order to teach this class, we of course needed a loom that was going to be optimized for classroom use. So different types of looms have different trade-offs in the quality and complexity that they can make cloth, and with the cost and time that you're going to take to purchase the loom and set it up. So cardboard looms are an example of looms that provide a lower quality fabric with limited pattern complexity, so they have limited ability to teach these mathematical concepts. However, they are very simple, they're very cheap, and they're very quick to set up, which is a good thing in a classroom. Shaft looms provide slightly more complex patterns with higher quality. However, they're going to take a very long time to set up in the classroom. They're a little bit more costly, so they're not exactly a feasible classroom tool. Commercial jacquard looms, on the other hand, have an even higher cloth quality, and they provide nearly unlimited pattern complexity. However, they're incredibly expensive, ranging upwards of $30,000 per loom, so they're not at all feasible in the classroom. An ideal classroom loom is going to have the high quality and complexity of a jacquard loom at a more classroom appropriate cost. If only we had such a loom. We do. DIY jacquard looms. In the past, researchers and hobbyists have made different DIY jacquard looms that are aiming to do just this, keep the complexity high and the cost very low. So they offer this high complexity and low cost. They also add an additional benefit of bringing engineering as a discipline that you can teach in the classroom. However, these DIY looms still take a long time to set up, which takes away precious time in the classroom. And so we aimed to build a DIY jacquard loom that would retain the quality and complexity of jacquard cloth while keeping the cost reasonable and the setup time low, so you can focus more on your target topics in the classroom. So we designed SpearLoom such that setting up and using the loom is going to be made quicker and easier for novice students to optimize the student interactions. The loom should be affordable for classrooms, and the designs should be kept open source so that they're more accessible in the classroom. And the loom should minimize tasks that don't contribute to learning math, engineering, or weaving so that it can remain interdisciplinarily relevant in the classroom setting. So from these design requirements, we designed SpearLoom. SpearLoom is a fully jacquard loom, meaning each of its 40 warp yarns is individually actuatable, so those are the yarns that are going throughout the loom. And this allows for complex patterns and their exploration and exploring their mathematical properties. So the jacquard mechanism also allows for switching between patterns without having to reset up the loom, which is going to save students a lot of time in the classroom as they explore many different patterns. The novel design of the tensioning system tensions each warp yarn individually, which is not very typical of looms at all. And this eliminates the need to ensure even tension across all the yarns by hand, which can take novices tens of hours to do, and that's going to save us a lot of time in the class. So once we designed and built SpearLoom, we evaluated it with respect to our design requirements against other available looms. So up here we have the TC2, the Jock 3G, and the Ashford Shaft loom. Those are all commercial looms that are available for anyone to purchase. And we also evaluated it against Albert All's loom, and that is another DIY jacquard loom. So in the case of setup time here, we want to lower the setup time again to make it faster in the classroom. So the blue bars here represent the setup time of SpearLoom, and you can see that they are less than or on par with the other looms. And with regards to our accessibility requirement, SpearLoom is lower in cost than the commercial jacquard looms, but it's higher still than other DIY looms, coming in at around $1,100 per loom. So this trade-off in cost is going to affect the speed of which the students can weave on the loom, as well as the quality of cloth that's being produced. So with regards to weaving time, shedding time here means that the lower the shedding time, the faster you can weave on the loom, so it's better to weave faster in the classroom. SpearLoom is shown again in blue, and it is slower than the commercial jacquard looms, but it is faster than other DIY looms. So this is a direct result of that cost trade-off that I was talking about. We chose an actuator with mid-range cost and mid-range speed to balance both of those needs in a classroom setting. The resolution of cloth pattern is also affected by the cost of the loom. So on the left, you can see the commercial jacquard looms have a very high resolution, making very high quality fabric, but again, they are very costly. And on the right, you can see the DIY looms have a lower resolution in the cloth that they can produce, but they are much lower cost, right? So SpearLoom lies somewhere in the middle, again, aiming for slightly higher resolution in the cloth in order to better see those mathematical principles and keeping costs reasonable in the classroom. So finally, to test the ability to support interdisciplinary learning with SpearLoom, we taught a class focusing on teaching math and engineering through weaving. So we had 13 total participants from our class, ranging from sophomores to PhD students. 11 of our participants were women, and the students had a range of backgrounds, including fine arts to computer science and engineering. We actually used these different interdisciplinary backgrounds in order to create groups of different disciplines for the students to work in throughout the course. So the course was 7 weeks long with 5 in-person sessions. We focused on, again, weaving, mechatronics, and linear algebra as they pertain to weaving. We paired each lecture with a set of activities in the class, beginning with students building the SpearLoom, and then designing and weaving patterns related to mathematical principles, and then finally the students worked in their groups to design an interactive textile for their final project. So during their final projects, all of these groups naturally approached the problem with an engineering design cycle mindset, integrating many disciplines along each step of the way. So they first began with some blue sky designs, creating artistic designs from cultural meaning. They then moved to feasible designs, where they determined what type of textile to make and the considered constraints on how to engineer that textile with SpearLoom. They then modeled their design, where they created a weaving draft using matrix multiplication. They then tested their designs using mathematical operations to determine the physical properties of their cloth, like sturdiness. So one group determined that their cloth was going to be too loose through those mathematical operations, and they could change their cloth before they wove it to actually ensure that it would turn out how they wanted. And finally, the students were able to weave their final projects on SpearLoom, seeing the physical product of the mathematical and engineering design that they had previously done. So through observations and interviews, students reported learning math and engineering through the context of weaving in a very interdisciplinary way. While students expressed satisfaction with the class, there was a few students reporting that they wanted actually more time in the course. We had a very limited amount of time to teach. So in our future work, we're going to be expanding the time of the class and expanding the topics that we have to offer throughout the course, as well as iterating on Spearloom to adjust for different notes the students had on student interactions with it and to lower the cost further. So in conclusion, Spearloom satisfied our design requirements through quick loom setup and weaving, moderate cost, and open source design. Spearloom supported the interdisciplinary instruction in textiles, mathematics, and engineering. Thank you all for listening, and I'll take any questions.
Thanks for the really great talk. I'm excited to look into the design in more detail. Super cool. So as an educator who teaches with digital fabrication equipment, one of the biggest costs I encounter both in terms of money and light labor is maintenance of the fabrication machines. I'm curious, like on one hand, like, do you have a sense of what the specific maintenance challenges, opportunities might be around Spearloom? And then something that I'm also excited about, like, to what degree did you engage the students in learning about maintenance and repair because they were building the loom itself?
Yeah, excellent question. Thank you. Like I said, all the designs are open source, so we made it such that in order to maintain, the instructors should be able to maintain it themselves. Most of the parts are either just purchased off the shelf or they're 3D printed or laser cut with all the designs being online. So if one individual part of the machine breaks, you can actually go and just replace that individual part of the machine. And during the course when the students were building the machine, there was actually a lot of talk that they had about like how they would design parts differently, and they really got to explore like the full design of the loom as they tried to fit two things together and maybe struggled with it. They thought about like, how could I design this differently? How could I make this better? So it was a very cool experience to see.
Cool, thanks.
Hi, thanks for the talk. My name is Camila. I'm from University of New Mexico. I was wondering if you could just talk a little bit about like the student experience and the different disciplines that they came from, and did you find that it was like the engineering students tackled more maybe difficult mathematical problems in their work, but the art students did like, you know, more complex fabrication, or did they like teach each other? How, I don't know, I was just wondering if you could talk about that a little.
Yeah, absolutely. And we talk about it a lot in our paper too, but I'll dive into it briefly here. We did actually have a lot of the students from different backgrounds sort of pick up on these concepts faster. So like you said, like the people from fine arts backgrounds had a little bit more of like the design and the weaving experience, and they taught the people in their group as they were going along. And it was really cool to see one instance of a group where one of the students had like the pattern design, a student in engineering came through and like explained all the mathematical concepts, and then there was another engineering student who explained like the electronic workings that actually mapped from like the design to their final pattern, and so they sort of like cyclically explained that to each other as they like wove on the loom, which was really cool.
Cool, thank you.
Thank you.
Last question?
Hello. Great talk. Thank you. I'm curious about the impact you think the quality of this loom had on the educational experience compared to, say, the cheaper DIY looms. I think you mentioned at one point something about it making the mathematical structures more clear, but I wonder if you could talk more about that, or if there were any other effects that this higher quality had on the classroom experience.
Yeah, so we aimed for a slightly higher quality in order to give students a better feeling of like satisfaction with their final projects. So you can see here, like the final projects are like pretty high quality, and the students were all very excited about making something that felt to them like an actual piece of cloth. But they also had the opportunity to sort of like look at them and sort of see the different mathematical operations represented there. And during interviews, that was something that the students like reported having seen and reported very much liking about the class.
That's great. It's exciting to hear that there is a feeling like authenticity of creating something they're excited about. Thank you.
Yeah, thank you.
Awesome. Why don't we thank Samantha again? Thank you. So if anybody happens to have like a direct line into Neil Stevenson, I feel like there's this amazing opportunity to kind of like extend from like the loom workers to like deep learning and AGI in some kind of like really fantastic way. based on this past talk. Anyway, up next, we're going to switch gears a little bit, and we're going to talk about Vega Prof. And so when you're actually deploying visualizations out in the world, you care a lot about performance. And one of the great things about languages like Vega, Vega Lite, are that they kind of make it so you don't have to worry about all the execution and all the things that are happening, but then you kind of get distance from the actual performance of your visualization. And so Junwan here is going to present Vega Prof, which is a way to help developers profile their Vega visualizations. So take it away.
Thanks for the introduction. Hi, I'm Junwan from University of Washington, and I'm presenting Vega Prof. Interactive visualization analysis have become a central tool in data-driven decision-making. When we build these systems, the goal is to help its user achieve their goals, to help them understand and act on their data fast. So to make great visualizations, we have to take into account the task, the data type, the domain, and apply design principles on them. In the era of big data and cloud data analytics, scalability remains a crucial problem for data visualization in practice. So we need to add more constraints for interactive scalability and effective visuals that are also perceptual scalable. Although we have a simple and straightforward metric for latency, but it can be affected by both the design and computation. Users may need considerable iterative efforts to explore the options that optimize the performance. But visualization at its core is just mapping data to visual properties, and luckily we have a lot of great visualization DSLs. For fast iterative authoring, they can usefully abstract away unnecessary details. Visualization grammars like Vega and Vega Lite provide building blocks to compose a wide variety of charts and interactions. Vega works in a way that there are levels of abstractions that unfold in a lowering process, and users of these DSL have limited visibility to code execution because that's how it's designed for. Domain experts who use Vega in their day-to-day life might still know little about the internals, as we've observed in our formative interviews. So without adequate tools, it's difficult to profile and introspect visualization specifications. Current practice investigate performance issues include testing in a sandbox environment or the Chrome step tool. The dev tool instruments the low-level function calls, but they can't help locate the problem in a way that makes sense to the domain experts. And the semantic meanings in the DSL building blocks have been lost in the process and hard to figure out from the call stacks. So in response, we introduced Vega Prof to help easy and effective time performance profiling for Vega visualizations. To help the users discover the root cause of bottlenecks, it's not sufficient to simply just measure function execution time. Instead, they need to understand how different parts of their code lead to performance costs and how they are grounded in Vega's intermediate representation, which is the data flow. This is achieved by bidirectional profiling map. So we add annotations during the lowering process and then trace the results back to its higher level of abstraction. And we allow for visual inspection with coordinated views in the live editor. The users will be able to interact with the code blocks in the main editor, the performance view, the data flow view, and also a table that record all the interactive updates. And also interacting with each individual view, update all the other views with the selections. So now we demonstrate with one of the use case. The background is that we implemented a custom Vega transform. So instead of transform the data inside Vega, we have the option to offload data queries to a backend database. And after running the specification, we're able to inspect the performance view which takes us to the most computational intensive nodes. And we're able to inspect the results of the queries and also the query string. Then the user can move to the charts and interact with it. So the updates will be recorded in the pause table. So and the user click on the pause table, and the performance view and data flow view will be updated with the relevant nodes. And the users are also able to directly interact with the editor for the code blocks. We conducted user study with 2 user groups, visualization engineers and also the original developer of Vega. All our participants heavily used and commented positively about how we connect the components, and the highlighting features help them locate and address the issues. From our observation, visualization DSLs could be further optimized, so we advocate for jointly designing future visualization DSLs together with their introspection tools, including debugger and profilers. And recommendations for performance improvements could also be added to those tools. And also, although the visualization engineers we interviewed interact heavily with the performance view, but they didn't really know how to start with the data flow view. And also the Vega developer we interviewed also agreed that the data flow view could be more of an expert tool. As for the future work, by expanding performance tracking to the scene graph, components of the resulting rendered visualization could be linked to VegaProof. This would be valuable for DSL understanding and learning. Many DSLs uses a similar learning process and data flow graph as an intermediate representation. So further generalization of our approach could enable performance profiling for a variety of these systems. And also these DSLs are also frequently generated automatically by computer programs at scale and in web application under different browser and cloud configurations. Future research could extend to profile the distributed performance of visualizations. Thank you. And our code and demo are available on GitHub.
So I have a question. So I wondered if you could, as you were talking, I was thinking, you know, I had always kind of understood one of the advantages of Vega and et cetera was that it kind of lowered the barrier of entry for creating really nice visualizations. And nice meaning a bunch of different things, performant and also, you know, according to visualization standards, et cetera. And then I was thinking, well, who is the audience that is both technical enough and wants to dive into profiling and improving performance, but is yet, you know, also kind of the audience that would benefit from this easier way to create visualizations? Does that make sense?
Yes, yes. So first of all, I created this because it helps me with my own project. So instead of just open a console and print out everything and try to expand through the JSON tree, this way of visualizing everything and easy to locate them in different representation really helped me. Also, I think that so visualization often are used as like the output or a way of presentation to to systems. So for a system builder, it would be easier to use like a DSL for the front end, but also they need to optimize the entire architecture and also to cross different stack and think about how they would interact with each other. So I think this would be helpful.
Awesome, thank you. Probably we're going to take 2 questions. Sorry, we're running late.
Hi, I'm Jimmy Lin from Berkeley. Very nice work. You mentioned at the end that you would recommend that DSLs be designed in the future jointly with their introspection tools. Could you give an example of how a DSL would be designed differently if that were to happen?
I think I'm not really an expert on that, but I think, so for example, SQL queries, I think it would be better if they can be designed in a way that it will work for people of different expertise. And when design those languages, when they add those features for profiling, it would be just easier for everyone. Yeah.
Okay, thank you.
Hey, thanks for the great talk. So one thing I was curious about, and maybe I just missed it, but I was really interested in that data flow view and its identification of kind of critical parts that are slowing down your program. But I'm kind of confused on what a user does with that information afterwards, right? So like typically, if I see there's a performance issue, I'm then left being like, okay, where in the code am I going to go to edit to kind of solve this thing? But with something like a declarative Vega spec, I don't necessarily know how a user still takes that information and modifies their specification to improve the performance. So I'm curious if you have any thoughts on kind of how the system can assist users in modifying their specs or figuring out how to actually fix the performance issue after identifying it. Thanks.
Okay, I think one example that might be too easy for visualization experts would be when you have like a heat map and you have the dots on top of them. And it's easier to see that when you remove all the dots, it will be rendered faster. But you can actually try that in the editor and help you figure out. Yeah. I don't know if that makes sense. And also there are different ways to write the data transformation in the specification, and adjusting the order could also help with the performance.
Okay, cool. Thanks so much.
All right, let's thank our speaker again. All right, so you have made it to the last talk. No offense to the rest of the speakers, but of course we've saved the best for last. And Vidya's going to tell us about a really interesting system that kind of looks at information retrieval, especially now that we're doing retrieval, more interesting retrieval over curated data sources and over visualizations. Also, you're very lucky to hear from Vidya because she was just at Viz in Australia. Now she is here, and then she's going to India in like a day or something. So, but this is the most special, I'm sure. So.
Thanks, Jeff, for the kind introduction. I'll try to wrap up soon if I can get my slides up before the break. And I swear it was working. Maybe I should take off my, should I take off the dongle, you think?
Has somebody already made the joke at UIST about how we do all this amazing work, but still the hardest problem is, yeah.
Or just use, oh, there it is. Yay! All right. Thanks so much for sticking on just before coffee break. So this is work done with Andre Kanyuka and Arjun Srinivasan at Tableau. Data repositories that contain a combination of curated data sources and visualizations can serve as rich sources of information to help with data discovery. However, a limited ability to express search queries and discover relevant content can make using these repositories rather challenging to navigate. So to better understand the types of search tasks people would find useful when searching over data repositories, we conducted a series of interviews with 14 participants and asked them to share their experiences when they search for data or visualizations, and having them discuss any areas of improvement. And so we identified 3 key user search scenarios. The first one was question and answering to support queries such as, how has the trend of movie budgets changed over time for different genres? Number 2, exploratory search to search for queries like election results in existing dashboards and charts. And number 3, design search to look for specific chart types such as stock data shown as tree maps. So based on this feedback and guidelines from prior work on search interfaces, we introduced Olio, which is designed as an interface that supports semantic search behavior by dynamically generating visualization responses and pre-authored visualizations. I'll play a brief video showing how this system works.
Here we see Olio's interface displaying a sample of available data sources along with pre-authored visualizations indexed from Tableau Public. Users can hover on data sources to preview the metadata and issue queries using the search box. In this case, on receiving the query, what are average budgets by genre, Olio peruses through the available data sources to find any relevant ones. Detecting a match with the movie's dataset, Olio then dynamically generates a sorted bar chart to answer the given query and produces a text summary describing the key takeaways from the chart. Besides finding a relevant data source and generating the dynamic response, Olio also returns 50 relevant visualizations. Users can skim through and explore these visualizations or leverage the dynamic filtering widgets to identify visualizations of interest. When unsure about its interpretation, Olio also gives users the option to override its default selection. Consider the query, show sales across the US. Similar to the previous query, the system finds a relevant data source about Superstore sales and generates a map since the query includes a geographic intent. However, Olio also indicates that there is another sales data source relevant to the query, allowing users to switch between the two. In the case of exploratory search like election results, where the input query is too vague or the system is unable to match the query to a data source, Olio does not generate a visualization. The system only displays pre-authored visualizations, allowing users to leverage the filters to explore the content. Coupled with the filtering options, the interface provides users the ability to search for visualizations in more expressive ways by directly specifying a chart type to look for, combining different visualization types, or even specifying lower-level graphical properties such as shapes composing the visualization.
So now let me describe how Olio works under the hood. So Olio takes as input an input search query that is passed to this query classifier, and the classifier supports federated query search, which is the process of distributing a query to multiple search repositories and combining those results into a single consolidated search result. The query classifier passes the search tokens to a parser, and the parser determines if the query contains any analytical intent, such as aggregations, correlations, temporal or geospatial expressions, and the query classifier also passes these query tokens to the semantic search framework to determine if the query tokens match fields in any of the data sources, such as prices, mapping to the price attribute in the housing data source, for example. The general search module displays thumbnails of pre-authored visualization content and enables 2 types of searches, exploratory and design. The Q&A module interprets the analytical intent expressed in these search queries based on the list of top matched data sources returned from the semantic search framework, and then dynamically generates visualization responses as seen in the Olio interface. Digging a little bit deeper into the semantic search framework itself, this framework primarily comprises 2 phases: indexing and searching content and metadata in the data repositories. The indexing phase creates indices for each of the data repositories along with their metadata, and then given a data source and the visualization content, each file is represented as a document vector. So given input query Seattle house prices shown here, This is represented as a query vector, and we encode the vector into string tokens similar to what is done in the indexing process. The search process retrieves the most relevant document vectors as candidates based on the amount of overlap between the query string token sets and the document string tokens from the data sources and the pre-authored visualizations. Olio finally ranks the vectors in the candidate search result based on a bag of words retrieval scoring function that ranks documents based on the query terms appearing in each document, the frequency of query terms within them, the length of the document, and the average document length in the entire collection. So using Olio as a design probe, we conducted a preliminary user study to qualitatively assess the overarching idea of combining dynamically generated visualizations with pre-authored charts. We recruited 11 participants for this evaluation. Overall, participants noted that this hybrid search paradigm was useful and could help accomplish their various search goals. Findings from the study showed that hybrid search results provide a richer analytical experience for both targeted and open-ended data exploration. However, there are plenty of interesting research directions to move this work forward. As people actively explore data and create analytical artifacts, we need to explore ways to support a broader repertoire of search goals within these data repositories. Search precision depends on the availability and the curation quality of these data sources, so future work should explore techniques to help with data curation, including metadata enrichment, entity recognition, and synonyms. Finally, trust is an important issue, especially when we're deploying these with enterprise customers or people with sensitive data, and users would benefit from information that communicates the provenance of these data sources and have built-in support for data privacy, both for indexing and searching of content. And with that, thanks for listening and staying on past the coffee break, and happy to take any questions.
For the record, I think we actually have 3 minutes until the coffee break, so if there are questions.
Hi, I'm Hitha. This is a really exciting talk. I was wondering if any of the participants indicated that a different modality of search query was preferred by them, for example, like a half-baked visualization.
Like text versus voice, or
text
direct
versus
manipulation?
voice, or maybe an image or some sort of half-baked visualization?
Yeah, that's a really good point. So specifically for design search, searching for visualizations, a lot of participants wanted the ability to be able to show an example and say something like that, because either they did not quite know how to describe what was in the visualization or use the right language, even though we did have some built-in common concepts for those. And so being able to extend this to search by example would be a great idea.
Awesome.
Yeah, thank you.
The University of Toronto. I had a question on the demo part where there are perhaps 2 data sets that might fit this query, and you could select between the visualizations generated from each. Sorry if I missed it from the demo, but does it also support, for example, combining the data from multiple data sets or wrangling them in a way that create more, I guess, complex or derived visualizations?
Yeah, so the system right now only searches, generates Q&A responses per, data source. But yes, I think future work would really be interesting where maybe there's a partial match to multiple data sources, and if they can be dynamically joined perhaps, or using a combination of the two, that would be great. Yeah,
I think that would be very cool.
We didn't implement that.
All right, yeah, thank you.
Awesome. Okay, I think we did it. So I promised you the best session at UIST, and we got it. So thanks to all the speakers.
Hi everyone, welcome. So we're gonna start this session off. So welcome to the session on words and visuals, authoring tools for text and images. I am Akar Gupta. I am a principal researcher at Fujitsu Research, and I'll be your session chair today. So yeah, it's the same thing, 8 minutes talk, 4 minutes Q&A, and please use the mics at the end of the talk for questions. Our first presenter is Stephen Braid, and he'll be presenting Promptify, text-to-image generation through interactive prompt exploration with large language models.
Great. Thank you very much. Yeah, so as mentioned, I'm Stephen. I'm from the University of Toronto, and I'm presenting this work that we created, Promptify. So it's a full-stack interactive system meant to facilitate the use of text-to-image models for novice users. So I made this system with my mentor, Brian Wang, and Mauricio Souza, and my supervisors, Sagi Vor and Toby Grossman. So I'll start by giving some motivation for this project. So text-to-image generative models have demonstrated really remarkable capabilities in generating high-quality images based on textual prompts. Models like Stable Diffusion and DALL-E, and also Midjourney as well, allow for the rapid generation of compelling visual content given a detailed prompt. However, crafting these prompts can be quite challenging. Oftentimes, it requires a user to align their creative intention with the model's expected behavior, making it important for users to understand the training distribution of these models to achieve the best results. This leads to laborious trial and error procedures to ensure that the model interprets the prompts in alignment with the user's intention. So, next one, there you go. So to address these challenges, we're presenting Promptify. It's an interactive system that supports prompt exploration and refinement for text-to-image generative models. Promptify utilizes a suggestion engine that's powered by large language models to help novice users quickly explore and craft diverse prompts. Our interface allows users to organize the generated images flexibly, and based on their preferences, Promptify suggests potential changes to their original prompt. This feedback loop hopefully enables users to iteratively refine their prompts and enhance desired features while also avoiding unwanted ones. So to show how we do this, I want to discuss our features in more detail. So we start with this subject ideation feature. So users can start with an atomic subject matter like a lion, for example. And from there, they can receive flexible suggestions that enhance the detail of their subject and its surroundings. This is done with a zero-shot prompt using ChatGPT. Here, a user might request, for example, that they might want to actually have the setting of this particular scene be in Japan, so they can use the subject steering feature in this particular case to actually modify this original prompt so that you get this lion standing underneath Mount Fuji. From there, they can also add style tags to their images. So this is via the style extension feature. So they can start with some atomic idea again here as well. So maybe they're thinking of something like Studio Ghibli, right? From there, this can be appended to their original subject parts of their prompt, and then auto-extended using a few-shot approach with ChatGPT. So these extensions are made using this few-shot approach, as I just mentioned. And the context of these is that we take examples from prompts from the Stable Diffusion community, so that when the LLM actually sees and is trying to extend this given prompt, they have context from what things actually work within the Stable Diffusion community itself. So in the interface, these suggestions are stored in a pop-up menu that's directly next to the text box where people actually type in their prompts. And here you can see that you get the subject suggestions in orange and the style extensions in blue in this existing menu. Okay. So, given an enriched prompt, users can now generate their images and use the layout and clustering features. This feature organizes and clusters images by their similarity, exposing common thematic elements, and also allowing users to zoom, drag and drop, and make their own clusters themselves. This visualization is largely navigated using a mini-map that's on the bottom right of the screen. So moving from there, given a desirable cluster, I'm just going to pause this video here. Given a desirable cluster or a desirable image, users can now refine their original prompt using the prompt modifiers or keywords that you can see in the menu in the middle of the screen here. These words in this menu are closely related with the image itself and are suggested using an open source model called Clip Interrogator. And when we append these different keywords into the existing prompt that the user has, the goal of this is to help them refine their prompt to move them towards their creative intentions. So if they see an image that they really like, and they select it, and they select a keyword that's closely associated with that image, by adding it into their existing prompt, they might be able to get more images that are what they want. So to actually evaluate the system, we completed a 14-participant within subjects comparative study that compared Promptify with a popular baseline called Automatic 1111. From there, we received subjective ratings after the users spent time generating images with either system. And after the comparative study, we also completed a series of free usage observations and semi-structured interviews, in addition to soliciting subjective ratings of each of the features that we've implemented in Promptify. So the results of this comparative evaluation show that Promptify requires less mental demand and causes less frustration than Automatic 1111, while also being rated as more useful. Additionally, our participants find that our system helps them generate more aesthetically pleasing images with their first prompt, but we did not observe that Promptify significantly helps users generate images that precisely match their creative intention. Additionally, our users find it easier to ignore undesirable images with our system, in addition to finding it easier to compare images with Promptify, suggesting that Promptify helps users manage large batches of images, which is very important when using text-image generative models. So here you can see how we might actually get this sort of difference in aesthetics. So at the top, you have the first attempt that our participants made using Promptify, and at the bottom, you have the first attempt using the baseline that we had. So this might explain why people felt that there was some difference in the aesthetics between the initial images, and I think this can be largely attributed to the style extension feature, which adds a lot of necessary context for creating images of a good style. So in our free usage observations and interviews, our participants described that our prompt suggestion engine somewhat sparks their creativity by suggesting details that they had not thought of themselves, while also enhancing the style of their images. Users also highlight how the layout and clustering features help them better organize their creative desires by organizing the images thematically. And the prompt refinement feature did see some success, but was not rated quite as highly as our other features. And in fact, we did not observe any statistical significance that would conclude that it enables better prompt refinement. However, our participants mentioned that the suggested modifications are often the names of artists that they don't recognize, so they may not have context for why they would want to add them into there, or that for subject-related keywords, they're often redundant and just repeating what's already in the image itself, so not making it super worthwhile for actually changing the original prompt. So I'll conclude with some insights and some future work. So to recap, we've created the system Promptify. It aimed to enable a workflow that helps users write prompts and then refine their prompts through visualization and specific suggestions of refinements for their images. We first exemplify how large language models can be used to facilitate the use of text-to-image models. In this system, our participants find specifically that they help them fill in details that they would not have otherwise thought of themselves. Our images also end up being more aesthetically pleasing with fewer tries, but we do not observe that our system helps create images that better match a specific creative vision. Better text-to-image models in future can enhance this by ensuring that prompts are followed, or systems as well can take different approaches for this sort of thing. Our approach to prompt refinement could also be improved to a certain amount. And in fact, what we recommend in the future work in the paper is that people use stronger visual language models like GPT-4 to better enable refinement of prompts. And in fact, if you have seen the DALL-E 3 demo, this seems to already be the case. And in fact, in some ways, this current approach and how they actually use this model could be viewed as an extension of our system, but I would not take credit for that in any way. And in fact, what you see is they actually have this prompt writing agent. So instead of having the users directly write a prompt themselves, there seems to be this interaction where from the chat, GPT-4 goes ahead and writes prompts for people by themselves. So what I look forward to seeing in future is this sort of exploration of agents versus direct manipulation of prompts. So like whether there will be still a reason to actually write a prompt yourself, or if it's better to use these sorts of agents. And additionally, I think there's also a lot of room to see how we can actually make really judicious use of these sorts of prompt writing agents in future at UIST 2024. So that's what I'm really looking forward to see. Thank you again all for your time. And I'm also looking for PhD opportunities and positions in industry as well. I'm just wrapping up my master's, so thank you very much. Thanks.
I have two quick questions. First of all, as I said before, I think this is a really interesting paper. Mm-hmm. In terms of objective text versus maybe a command, have you looked at all if there's something that is asking for action, so it's a call to action? Have you looked at all at that? And I think maybe this weaves into that. It's a subsequent question, but maybe it weaves into that. There was another paper that was presented earlier this week called, I don't know how to pronounce it, it's Visar out of Notre Dame, that looked at creative writing and using LLM models to to stylistically enhance creative writing and presenting the alternative argument, maybe a responsive argument. Have you thought at all, I mean, I saw in some of that, sort of those themes on that last slide, sort of future work, how that might weave in. Did you look at that paper at all, or that kind of like thinking about like the context and the counter argument, or how else you might look at it in using LLM models to help prompt engineering in that way?
So I haven't seen the paper that you've mentioned. I want to ask, what do you mean by call to action?
So if I said, so you said on there, I forget what the prompt was, but like the dog versus have the dog bark or bark, something like that. Because, so just as context before, like I'm working in autism, there could be uses, and I think there's also technological uses for for something that is a command or a reference to some activity versus something that's objective.
So so there's a work that we cited in Promptify, which was, I believe, by Vivian Liu at Columbia University, I think. And the context of what they did is they explored what words are actually focused on with these sorts of text-to-image systems. And in terms of like a call to action, like if you said a dog barking, it might work. And I'm sure the newer models can definitely help with this sort of thing as well. But in general, they seem to focus in on specific keywords. So action specifically might be tough to actually get it to do something like that, but it could be worked on.
But if it said the dog is, I don't know, the dog is pretty versus the dog is not pretty, would it change the image based on that?
Certainly, certainly, yeah. Anyways, we can talk more about that later. Thank you. Yes? Oh, sure. Oh, are you Vivian?
Yeah, hi, I'm Vivian. I'm from Columbia. I really like your talk. I
Thanks.
think that your technique is something that I think a lot of industry companies are picking up on, this prompt expansion idea. My question is, there are other models that are capturing style in non-linguistic terms, like LoRa's, that capture concepts, like, for example, a type of anime character look. So I'm wondering, does this technique extend to those sorts of models?
Good question. Off the top of my head, I'm not sure. I think what can work and might be possible is like with a model like Stable Diffusion, for example, the conditioning of the model is based on clip, right? So you could imagine that if you had a group of images of a particular style, you might be able to get some sort of embedding from all of those images, because with clip you can generate embeddings for both images and text. So I think that could work, but I'm not sure I think maybe you'd have to have like a larger database of images, and from there you could like pull on things of a particular style and ask people if this like matches with the style that you're expecting or not. But in terms of the actual technique that we use specifically here with extending the prompt itself, you might need to like, I don't know, like there are people who do like this sorts of like training of specific models, and you end up getting like the ID tags that summarize a particular style. So maybe that could be embedded in the system in some way. I'm not actually sure, but I'd love to talk about it more afterwards.
Absolutely, thank you.
Thanks.
We have time for one last super quick question.
Maybe we'll continue this offline, but I'm curious if you observed any interesting, to your mind, changes in the design process as a result of the work that you did. For example, were people creating more images using Promptify than they were using Automatic 1111, or were they looking for specific, like were they doing their prompt explorations differently as a result of how you built the system?
I think like at the simplest level, yes. So people would just they would just think of like a subject matter and be like, okay, I want an image of a tiger, right? But they wouldn't necessarily think of like a tiger stalking prey, for example, right? But I think one interesting thing that ended up happening in the user studies as well, so that was an advantage, and people really loved that. But I think part of the work that can be done in the future is like, if you have this suggestion, how do you guarantee that you can actually show a tiger stalking its prey, for example, right? So as much as you can say like, okay, I really like this sort of extension that you've given me, it's very difficult at times to actually make that happen in practice. But I'd love to talk about that later. I'm not sure I understood the question 100%.
All right, thanks, Stephen. Our next paper is PoseVec, authoring adaptive pose-aware effects using visual programming and demonstrations. And it will be presented by Yongji Zhang. Take it away.
not showing. Maybe try the other ones. Oh, it's, I think I need to see. Yeah, yeah, thank you. So thank you for waiting. Hi everyone, I'm Yongqi Zhang, and I'm a PhD student from George Mason. I will be presenting our research paper, offering adaptive post-aware effect using visual programming and demonstration. This project is my summer internship project at Adobe, and it is my pleasure to work with our amazing collaborator, Con and Rubias, and also my research advisor, Professor Craig Yu. So let me quickly ask you a question. Raise your hand if you have played with AR filter before using either Snapchat or Instagrams. Okay, I see some hands. I hope you can find out two useful at the end of our talk. The kind of visual effects we interact with on a daily basis is human-aware motion graphics, and our research is focused on subset of it, which is the type of effect triggered by body motion. We call it pose-aware visual effects or pose effect in short. There are many applications for this type of pose effect. It can be an exercise circuit that helps you count your repetition while you're doing exercise. It also can be an interactive tutorial that teaches you how to play tennis and correct your posture in real time. However, often this kind of pose effect is not easy. Traditionally, we use video editing to create pose effects, where the animations are break into video timeline. As a result, the output of this effect is non-adaptive, meaning it cannot be reused on a different video. Recently, there are programming-based tools such as Lens Studio and Spark AR that can help users to create adaptive pose effects. However, this approach requires substantial amount of programming and configuration, which might be a challenge for non-technical designers. Thus, we want to simplify current programming workflow so that novice users can create complex and reusable pose effects while doing low-level programming or keyframe editing. Previous works used programming by demonstration to create different AR applications. However, their workflow and user interface are not designed for offering adaptive animation based on pose data. We extended for a pose effect offering. So we present PoseWeb, a web-based offering tool that combines programming by demonstration and visual programming to support pose effect offering for novice users. Specifically, PoseWeb enables direct manipulation on video canvas to streamline the offering process and use node-based user interface to simplify programming complexity. So let's use PoseWeb to create a pose effect for this squat down exercise. There are two effects happening in this video, but I just want you to focus on the effect on her left knee. This effect shows the angle of her left knee as she squats down. In our node programming design, we follow data programming model and define find times alone. I will show you how PoseWeb to use this type of node to create the effect. First of all, we need a trigger to initiate the pose effect and the animation. This trigger is usually a pose recognition function that outputs a signal when a specific pose is performed. In Postweb, designer can easily create such trigger through direct interaction with the video canvas without worrying about all the low-level detail. This is because our post recognition nodes use view invariant one-shot post embedding network for post recognition. Then, we need a logical condition to control the timing of the appearance of this post effect so that it only appears while the person is scrolling down. Here, we add the during node to represent this logical condition. In general, logical node in Postweb encode a variety of logical conditions. Now, the only thing left is to create post effect that display the joint angle of her net knee. If this were programming, we will use a variable to represent post-related information, which will be used by a render function later on. Similarly, we define data node, which will be actively monitor the skeleton pose on the video canvas and compute and output post-related information. Here, we use joint index data node that represent the net knee joint information. Other post-related data, including joint location, distance, angle, or even post-embedding vectors, are also supported by Postweb. To render the effect, we need a render function that computes joint angle of the selected joint and display the information near that joint. In Postweb, we had defined joint angle annotation node to represent this functionality. And once these nodes are connected, we could see the render effect on the video canvas in real time. In general, render nodes represent some render functions that are executed on a group of graphical objects. Other render functions, such as object placement, object movement, color changes, and so on, are also supported by our tool. Once the user finishes the design, the output post effect can be used on a different video or in a live cam with minimal or no configuration needed. In this way, user can create reusable template effect rather than break-in effects. We evaluate our tool through a qualitative user study and a replicated example study. For the qualitative user study, we recruit 12 participants who have some programming and visual effect creation experience. We provide training and ask them to use Postweb to create a post effect. Here are some examples they create in 1 hour. We require 3 complex post effects from the example for this study, but I only want to show one of them in this presentation. This example is based on an online kinetic typographic collection. In this effect collection, the text "Just Do It" is stylized and animated dynamically to different athletic poses. We create an example following this style. As you can see, user control the style or "Just Do It" text by performing a jumping jack pose motion. It also showcases the output pose effect is adaptive and can be reused on many different videos. So to sum up, we present Postweb, a lightweight web-based offering tool that combines programming by demonstration and visual programming. We implement video canvas to allow users to create post recognizer directly from the input video stream and obtain low-level post information from the nodes. We have the node programming interface, which allows users to quickly test and refine the post effect program. Together, we support non-technical designers to create this adaptive and expressive post effect. This is the end of my talk. Thank you for listening. And I also open to any internship opportunity.
All right, while people are thinking of their questions, I have one. Great talk. So essentially, what the examples that you showed, most of the poses were sort of people doing an exercise or something like that. What will happen if people are interacting with their environment, like punching a bag or some like dribbling a basketball or something like that?
So you want to create an effect that is interactive in environment?
Yeah, and then how would that transfer to another video, as you said?
Okay,
yeah.
So currently we did not suppose that because we only focus on post-effect offering, but is it possible to extend our current approach because we are using a programming demonstration and visual programming to do the post-effect offering. Is it possible to adding more nodes, for example, the node that could be obtaining the environment information, such as depth estimations, and then from that we could create more adaptive post effect. For example, the effect could be when you walk closer or far away from the camera, you could potentially trigger an effect.
Hi, thank you for the talk. It seems like part of your motivation was that visual programming environments are simpler or easy in this domain over textual programming languages. And I was wondering if you looked at that question specifically in your evaluation, and if so, how you evaluated that, of whether these node-based programming environments were actually easier or simpler, or whatever the language you were using, over the textual environments.
Okay, so we conduct, so our first study is a first use study, which we inviting the people who have some program experience, but they have more visual effect creation experience, and then we just give them the tutorial and ask them to create post effect. And then we have asked them to, in the end of we have to conduct an interview. We basically also asking some rater question to ask them whether they found our tool is easier than their current workflow, and most participants say yes. And those are for the novice user, but for more experienced user, they want to have more advanced feature, which our tool cannot currently support, but it is possible to extend to that. Yeah.
Great, thank you.
I hope I answered your question.
Great. Let's thank our speaker again. Okay, our next paper is Wakey, animate text by mimicking characters in a GIF. And it will be presented by Ching Yu. He is not one of the authors, but the authors could not be here. So yeah, take it away.
Here. So you have me? So yeah, take one picture. It's not the same part in the moment. Yeah, it works. Yeah, hi everyone, I'm Chen Yuguo, a PhD student from UIST. I'm presenting the paper Wiki, animating text by mimicking character in a GIF on behalf of the authors from UIST, Fudan University, and MSI, who unfortunately cannot make it today. So the authors invited me to present the paper because we have some frequent discussion on the project, and I will try to deliver their lovely work accurately. Okay, let's start. So this work is rooted in the prevailing application of kinetic topography, meaning the animated text as part of the motion graphic design, So you may see this vibrant text in films, lyric videos, and also the advertisements, which can effectively deliver the subtle emotion of thematics through the text animation. So with WikiWiki, one may make a video opening like this. So you can see like the text can move according to the GIF. Generally, to create a kinetic topography is not easy. Creators can turn to complicated animation software and carefully design each keyframe and also arrange the timeline. But when the design intent is fuzzy, for example, to convey a cheerful mood, it's often time-consuming to craft a kinetic topography from scratch. And available instances lack flexibility for new combination of letters, since many animated effects may lead to the deformation. But on the contrary, intuitively, it's relatively easy to find a meme GIF or sticker with motion matching the intended web. So intuitively, this work explores a way to animate text in a similar manner of an anchor GIF so that the intended semantics of emotion can be expressed. Transferring from the GIF motion to the text animation can be regarded as a motion transfer problem that has been widely studied. However, existing approaches are largely based on a given object model, so meaning that both the static source and the video target, they share similar structure with clear specification. So in recent years, there emerges approaches featuring model-free motion transfer, but they operate in the raster domain rather than may not generate well for the text. So in summary, there are two challenges to animate text by mimicking the GIF. The first one is to construct a mapping between the static text and also the target. And the second one is to maintain the legibility of the text. So this work proposes workflow to accelerate the generation process. The input is a target GIF and the static text, and the output result is a kinetic topography mimicking the motion of target. So there are three computation modules that address these two challenges, and the creator can also get into the creation loop by tweaking the algorithm output and also some details. So here is a demonstration with the driving GIF and the static text. Cross-domain motion transfer is first applied to extract the motion key point of the source and target in a supervised manner. So it animates text in the raster domain. And then the colorful motion key points are mapped to the vector control points of the text using the affine transformation and optimized locally to maintain the relative position of adjacent control points. So in this way, the static text will wake up. So this is an author interface using this approach. The user can first specify the text and the drawing GIF, and then manually adjust the motion key points, or directly manipulate the control points on each keyframe. So this is a demo of a plugin that can support the real-time generation of the animated text in the online chatting scenario. So the user can set a GIF and also set a text, and then they generate a animated text and also send it into the Slack. To ensure doing the right thing, so this work also conducted intensive evaluation. The application study examines each computational module to evaluate their contribution to a satisfying result. And the case study investigates whether the approach reliably produced a legible result. And the questionnaire study takes a step further to validate that the essence in the target GIF is indeed preserved in the generated kinetic topography. And the user study investigates the authoring experience of people and their perspectives of the application. So I will selectively discuss some interesting findings. For different target GIFs, the automatically generated result is the most stable for a clean background with only one simple object. So to scale to more diverse GIFs, we can enlarge the training data set of the backbone model or integrate with some like the large vision model. And for different source static text, the approach works the best for fonts with many control points because more control points ensures more stable local structure. And the text length also matters because it determines that whether the text can look like the target. And also in the user study, after trying out the system, participant acknowledge its practicality in formal scenarios like presentation or some casual scenarios like work making. They enjoy customizing their text, seeing the value in personalized expression, and they find the creation process pleasant and efficient, which strikes a balance in agency and automation. So this work has two major limitations. First, the text deformation may not be stable across frames. Future work may consider propagating the vector control points or leveraging large vision model. And second, the animated effect is limited to deformation and motion, but there are more to consider in kinetic topography design, as summarized in the first author's other paper. Future work may also investigate animating multiple text and transferring the visual style like colors. So let me share some takeaway messages. This work demonstrates an approach to support the high-level authoring intent on thematics or emotion with cross-domain reference, and it allows editing with intuitive intermediate results, which reduce the fine-tuning effort. So thank you for your attention, and here are more demos. So I encourage you to take a picture of the QR code. It's a slidable page. The author will reply to your question after they saw it. And I will try to take your questions.
Question? Hi, I'm Kong from Adobe Research. Cool work. Just curious if you guys tested this on symbolic languages like Chinese, Arabic, Korean. Did you see the same result?
So basically the testing words there for free. So you can use like Chinese character or English character. So basically the user study, I know the user study is like recruit some students and they can use this like for a certain period and they report their user experience in different scenarios, like reading the vlog or some presentation or other cases. Yeah. Does it answer your question?
Sort of. We can talk offline. Really nice result, by the way. Thanks.
Thank you.
Yeah, thanks. Yeah, cool talk. I'll ask one. Basically, you're manipulating control points, and that's great, and giving the user that freedom. How would you, like, for example, if I don't, what I want to do is not want to control the control points, but do some sort of semantic editing, where I just want it to be more bouncy, right, more bouncier or something like that. And would that be something that you think the system could be extended with, which is some sort of semantic level of editing? And would that be helpful or not in this case?
Yeah, good point. Yeah. So actually, they're also extending their work to a more powerful way. So hope your suggestion will also be considered, and I will deliver a suggestion to them. Thank you.
All right, great. Thank you. So our next paper is Usable and Fast Interactive Mental Face Reconstruction. And the presenter is Florian Strom. Florian is currently a fourth-year PhD student, and he is on the job market. So please reach out to him after the talk.
Yeah, thank you for the introduction. So I'm Florian Strom, and I'm happy to present our work on behalf of my collaborators, Mirai Bace and Andreas Bulling. Our paper is called Usable and Fast Interactive Mental Face Reconstruction. So mental face reconstruction is the task to visually reconstruct an image of a face that otherwise only resides in a user's mind. And this is an important task for many decades already, and it's mainly used in police investigations, for example, when you have a witness and you want to create an image of a perpetrator, for example, from the witness's memory. Now, old methods, as you can see here, used like facial feature catalogs where the witness then could select the correct hair, nose, mouth, and so on based on their memory. Now, more modern techniques like SIGCHI utilize deep learning methods that allow users to generate a variety of faces and to iteratively combine them or manipulate specific attributes of those faces until they converge towards their mental image. Now, what all these prior works have in common is that they give the user the explicit task to reconstruct their mental image with this tool. And this is a really difficult task for the user. They have to use really complex software. It's exhausting, slow, often requires expert guidance. So instead, we propose our new mental face reconstruction system, which takes this burden away from the user and we instead give the user a simple auxiliary task, which is to only rank 6 faces that the user sees according to the similarity with their mental image. So they simply have to, via drag and drop, rank 6 faces from most similar to least similar according to their mental image. They can then confirm their ranking, and then the system shows 6 new faces, and the user repeats this process multiple times. And after a couple of iterations, our system combines this information from the previous iterations and proposes a set of possible reconstructions that the user can then choose from. So let's have a look at our high-level overview of our system. So in our case, we perform a fixed set of 20 iterations, and you can see on the top, for each iteration, we have 6 auxiliary faces for this auxiliary task of ranking them. And also we have the corresponding latent vectors that generated those images. So we utilize a pre-trained face generative model that can generate realistic faces based on those latent images, latent vectors. Then we have the user that ranks those faces according to the similarity with their mental image, and we keep track of the latent vectors accordingly and input those ranked latent vectors into our reconstruction network here in green. And this reconstruction network is a neural network that we need to train. And the task of this network is to take these ranked latent vectors as an input and predict one latent vector that, when we decode this, results in an image of a face that ideally resembles the mental image of the user as close as possible. Now, the core challenge to train this reconstruction network is data, because if you think about it, to generate one data point, we need to have a user memorize a face, so we have the target image, and then they have to rank 6 faces for 20 iterations. So this can take multiple minutes, so collecting a data set of thousands or even tens of thousands of data points is simply infeasible. So instead, we propose a user model that simulates the user, and this model also takes the auxiliary faces as an input. In addition, it also takes the target image that we can set freely during training as an input, and then ranks those auxiliary faces just like the human would do, and then outputs the ranked auxiliary faces. So I want to dive a bit deeper into this user model, how this works. So at the core, we have a face identification network. These networks allow us to extract embeddings from face images, and we can then compare faces based on these embeddings. Now, these face identification networks are typically trained with pairs of images. So, for example, we see here images of Obama. These are different images, but the same person. So we want the embedding to be the same, ideally. And when we have pairs of images of different persons, we want the embeddings to be further apart. Now, this already allows us to some degree to compare faces, but this is actually measuring face identity and not similarity. That has been shown in prior work that there's a difference there, because when you have a really similar looking face, but it's a different human, then these networks can generate embeddings that are far apart. In our case, we want to have similar embeddings for similar looking faces. So what we did is we collected a data set online with over 200 participants, where the participants were instructed to memorize a face and then rank other faces according to their similarity with this target image. So basically we get data of similarity between faces, and we can then fine-tune this face identification model such that it measures similarity. So when we have similar faces, we get similar embeddings. And with such a model, we can build our user model simply by extracting all the embeddings from these 6 auxiliary images and from the target image, and then we can rank the 6 images based on the similarity in the embedding space to the target. And we also show that this is in line with human judgment. So then basically we can use this user model to create an infinite amount of training data and train our reconstruction network. And then we put our system to the test. We run a user study with 12 participants. The task of the users was to memorize a real face that you see in the top row. And then we asked him to use our system and SIGCHI, the state of the art, to reconstruct the mental image that they just memorized. And we can see that when we look at this reconstruction, qualitatively the results look similar to the target face for both our method and SIGCHI, and these would help in, for example, police investigations to significantly narrow down the search space. In addition to these qualitative results, we also have 5 quantitative metrics. First, let's have a look at the 3 rightmost metrics: system usability scale, NASA TLX, so mental workload, and time required. And we can see that for those 3 metrics, our system significantly outperforms SIGCHI by a large margin. In addition, we also want to quantitatively measure the visual reconstruction quality, and for this we propose the mental rating and the visual rating that you see in the first 2 columns. So the mental rating, we asked the users to give a rating from 1 to 7 on a Likert scale, only showing the reconstruction. So they only see the reconstruction and they have to compare it to their mental image and give a rating from 1 to 7. After they give this rating, we then show them the true target again, and they can visually compare side by side the target with the reconstruction, and then they give another rating from 1 to 7. Now, if we look at the results for our method, we see that mental rating and visual rating is actually basically the same. There's no significant difference between the two. Now, interestingly for SIGCHI GAN, we see that there is a significant difference between the mental and the visual rating. So what this means is when participants were shown the actual target again, they typically on average lowered their rating that they gave before when they only compared to their mental image. Now, this gives hints towards some phenomenon that's happening when they use SIGCHI GAN, that somehow their mental image might be altered. We even, in interviews after the user study, multiple participants said that they were even surprised when they saw the target image again because they thought it would look different. So maybe we suspect that when using SIGCHI GAN, they always see the current reconstruction and they try to improve it and modify it to match their mental image. And not only does then the reconstruction basically converge towards the mental image, it seems like the mental image might also slightly shift towards the reconstruction. So this is definitely interesting for further inspection because this is something that you definitely don't want to happen when you want to reconstruct an image from witness's memory. And we cannot observe this behavior with our method. Right. So in summary, we propose a novel mental face reconstruction system that utilizes user feedback from a simple auxiliary task. Right? They only have to rank 6 faces instead of actively reconstructing their mental image. And we show that our system is really easy and fast to use. You could even imagine having a simple mobile app where they can drag and drop around faces and within minutes generate their mental image. Yeah, thanks for the listening, and I'm happy to take any questions.
Oh. Hello, Jeremy from Stony Brook University. Very interesting work you have here. I was wondering about, you mentioned that you have a reconstruction model that takes the latent codes as inputs. I was wondering what the benefit of that is, since you already have the latent codes, why are you using the network for the reconstruction network rather than if you have the ranking and there's a top face searching the latent codes around that area?
So we use this model so that it can basically figure out from which phase, which features are important. So it can basically see, okay, in these 5 iterations, the user always maybe ranked this phase as rank 1, and all these 5 images have like really similar eyes, so it can maybe figure out, okay, these are seen to be eyes that are relevant. So it can implicitly figure out which features from which phase are relevant by having basically positive examples rank 1 and negative examples rank 6. And I think without a learning mechanism, it's really difficult to define I'm sure there's a method to define an algorithm to combine this information to also get reconstructions, but I think a learning-based method can utilize this feedback from the user more efficiently.
All right, thank you.
Hi there, this is super fascinating. I know that models like this can be subject to bias when working with human faces based on gender, age, race, and other characteristics like that. I was curious whether you took any steps to try to address possible biases, especially because this tool is designed to be used in situations where criminals and identifying criminals.
Yeah, certainly. So our system definitely has biases. We also observe them because we rely on a pre-trained model called StyleGAN2, which is still state-of-the-art for face generation. And it's trained on a dataset called FFHQ flicker faces. And for example, this dataset mostly contains faces of white people, so StyleGAN is biased also to generate faces that tend to be like depicting white people and also more male people, so there's definitely biases. And within our system, we didn't have anything, and we didn't put anything in place to counteract this. So if we assume to have a bias-free generator, then our system would also be bias-free, but we are subject to the biases in the generative model.
If I can quickly follow up, do you have any ideas about ways that your system might be able to future work to address that?
I don't know. I don't have an answer for this. I think
Fair
I didn't
enough.
think about it. We can maybe discuss it more.
Yeah, thank you.
Well, thank you.
Thank you. So, looking at the results, my impression is that people are very bad at reconstructing faces, and I don't know if that's because the users are bad or the system is limited. So, have you tried asking people to reconstruct a face while looking at it to see if they were able to actually reconstruct it? So not just from memory, but looking at the image and then trying to reconstruct it.
No, in our user study, we only asked them to memorize it, and then they couldn't see it anymore. But can you maybe repeat your question, why you would want to evaluate on
Because it would tell you whether it's a system limitation or user limitation.
I see. Yeah, that's definitely interesting. We didn't consider this, but yeah, this would, yeah. Thanks.
Last super quick question.
Okay. So my question was, how do you start the user study with the first set of 6 images or something? Because, if you're like male versus female or long hair versus short hair or like blonde versus brown or like ethnicity, that's really quickly easy for the user to describe just like typing a word. And how do you quickly narrow that down in just by images?
Yeah. We didn't show this in the presentation, but we actually use some prior information, so we use gender and age, and then we prime our system with these 2 attributes. So participants memorize the face, and then they say, okay, it's a young female person, and then our system is, the faces that are generated by our system are biased to this category.
Okay, yeah. Thank you.
Thanks.
All right. So our next presentation is Spellburst, a node-based interface for exploratory creative coding with natural language prompts. And this will be presented by Tyler Angert. He is a designer at Replit. Also, his co-author Miroslav is in the audience and is looking for internships. So please reach out to him.
Oh. Okay, we're getting something, maybe. Use this mirror. Okay. Let's plug directly in. Oh, we got it. We got it. All right, the swag. Okay. Not starting yet, just test. Okay, cool. All right, thank you for the introduction. Hello, everybody. Once again, I'm Tyler. I'm a design engineer at Replit. And today I'm joined by my collaborators from Stanford University, Miroslav, Jenny, Christopher, and Hari, who all worked with me on this. And today we're going to be talking about creative coding with large language models. Hope you enjoy. So San Francisco is a beautiful city. And if you've been here long enough, during certain times of the year, a fog rolls in through the morning, and this fog has a certain name. Its name is Carl. And when I see Carl, I'm usually pretty inspired, and I might
take the initiative to make a new creative coding piece inspired by this scene. So how would I start this today if I saw Carl and I wanted to make a piece? Well, first, I might have an initial idea where I'm trying to outline, the general shapes of the clouds, the shape of the bridge, but I'm just trying to get a general overview of the scene so I can have a good base for my coding setup. But I know that creating organic-looking shapes and making it look realistic and interactive is usually pretty hard, so I'll start by searching for examples online. Once I find a suitable example, I'll take the code snippet, I'll open up my favorite editor of choice, Replit, and I'll put it in and I'll iterate and tinker on it until I have a result that I'm satisfied with. And then after a little while, I'll probably fork and I'll branch and I'll make a few different variations of my work, exploring different visual directions, different textures, whatever. And finally, I'll pick and choose the bits and pieces of each of the pieces that I like, and I'll merge it into some final artifact that I can share with my friends. And this is basically the ideal flow using today's tools, where you basically go through each of these phases one by one, and then you end up with the final artifact. But as we all know, exploratory work is very messy, and it doesn't really match up with that ideal flow. It's nonlinear, spontaneous, and you often have bursts of energy and motivation. It's hard to figure out and predict where along this timeline you might actually fit in. And this might feel familiar to a bunch of people, where we have tools that are available to us to help us track our work, but eventually you get lazy and your commit messages look weird. Your desktop is filled with hundreds of screenshots, and you just start duplicating files over and over again because it's easier to track mentally. But even with all of this, you end up trying to connect the dots all over the place to figure out which commit and which branch are linked to which file versions, are linked to which screenshots, and you're doing all this mental overhead just to figure out how your variations of work are progressing. And you look like a crazy person. This should not be the case. And all of our interviews with expert creative coders expressed these same frustrations, and they can be summarized as follows. One, it's really hard to go from idea to code, from a cold start problem. Two, it's really hard to create and track the variations of your work. And three, especially with vastly different divergent paths of work, it's hard to compare and combine them together. So to address these problems, that's why we created Spellburst. So let's take the same creative coding task as before, and let's do it on the Spellburst canvas. So instead of searching for initial references, I just have an idea and I know what I'm looking for, so I'll go onto the canvas and I'll create a generate node and just enter a prompt. I want moving clouds like Carl the Fog. And after running it, I'll see a generated sketch appear on the canvas. In this case, Spellburst has returned to me a complete P5.js sketch that's running on the canvas, and GPT-4 is being used behind the scenes to actually create this. And you might look at this and think, is this really doing anything that different from just using ChatGPT and whatever editor I have? I enter a prompt and I get it, and then I just see the output. In order to address this, we want to give artists more control that is something in between just a prompt and raw code. And we have a feature called semantic sliders. And basically the idea here is that you can take important parts and portions of the prompt that you specified and see how they're mapped to the internal state and global variables in the produced sketch. And this way you can have more granular control over the actual output in real time without having to be overwhelmed by looking at the entire bit of source code that's generated. That being said, if you are comfortable coding and you want even more granular control, there's also a built-in live code editor where it live refreshes the sketch on the canvas on every single keystroke. So you can traverse every level of abstraction. Now, I can keep adding modify nodes and training them together so that I can continue modifying the sketch. But there's still a cold start problem if I don't know what direction to go in. So I can say make it more something, and when I hit slash inside of here, I'll get autocomplete results from Spellburst that don't necessarily suggest the most correct thing to do, but just offer me interesting different directions to go in afterwards. So in this case, I'd say, make it more pointillism inspired. And I can actually repeat this process multiple times in parallel and see the results stream in. So here we can see that I can branch off from my initial sketch on the same canvas
and I can see and explore multiple visual directions at the same time. And then branching off from that, I can also start a completely parallel track of work where I'm looking at an image of the actual Golden Gate Bridge, and I'm doing it independently of my initial tree of sketches with the clouds. Now, I have these two parallel tracks of work, and I'm like, how can I combine them together in some interesting and meaningful way? And I'll use what's called a merge node, where if we zoom in, we can see that all I have to do is connect the two sketches that I'm going to put together, and I just say what I want from each of them in the final version, and Spellburst will combine them in a semantically meaningful way. This is basically impossible today with traditional merging algorithms because they're designed to operate on versions of files that are really similar to each other. If you tried to do this with two actual completely different sketches, you would get merge conflicts and you would have to figure out how to actually combine it manually. But language models don't have that problem. Now if we zoom out, we can see a lot is happening on the canvas, but three main things were addressed. One is that version control is basically baked into the experience of actually using the app. Two is that LLMs help bridge the semantic syntactic divide, helping you traverse different levels of abstraction. And finally, new kinds of divergent and convergent exploration are now possible through branching and merging. So in order to actually build this, one of the first things that we did was crowdsource a study with 52 experienced artists where we showed them two images side by side where they had to describe what they thought was the difference between the two. And that way we built up a data set basically of how people think about visual changes between interactive artwork and then also have the code to compare. And then we used this data set to curate a set of high quality responses of diffs between samples and use that for our few shot examples for prompt engineering that was fed into our autocomplete system and our merge and generate operations. And then for our evaluation study, we looked at 11 expert creative coders and did within subject comparisons. And we gave them a set of open-ended creative coding tasks, either using Spellburst or ChatGPT plus any IDE of their choice first. And one of the most interesting things about the evaluation studies that we saw was that using Spellburst, people explored vastly different paths that they would have normally, especially much faster. And they explored ideas that basically would have been impractical for them to try to experiment with and work on otherwise. So overall, artists liked Spellburst for three main reasons. One was fast prototyping, like doodling on a napkin. Two is the speed of the large creative jumps they could make that felt like similar to how they would normally tinker with code at a granular keystroke level. And three is version control, or rather the lack of it, in the sense that they don't have to think about it. It's just a part of the canvas. And secondly, artists had mixed opinions overall about ChatGPT and large language models, conversational UI for small creative jumps, where verbally describing what you want often feels like overkill. And secondly, several people expressed concerns about the ethical use of LLMs that we're all dealing with as a community, especially surrounding accreditation and implicit biases in models. So in the future, we'll add a few things mainly focused on bidirectional editing, so more direct control between the source code and controls in the UI, looking at more collaborative exploration, something more than just throwing a bunch of cursors on the canvas together, and then also looking at Spellburst in learning contexts like intro, design, and CS courses. So happy to take any questions, and we'll be releasing the code soon. Thank you.
Two questions. So in the demo, there's some of the prompts that, or at least some of the modifications were like similes and metaphors. Mm-hmm. How does it interpret like descriptive language versus like a simile and metaphor? Do you think does it understand that? And then the other thing is in the poster session right before here, there were right next to each other, I think they were both from KAIST, the using artistic means in AI and LLMs, or maybe AI, one for protein drawing, and then the other one was more like sketching in the auto sector. Do you think there's did you see those before this, and is there any application of this with like something maybe less creative per se and something like in like protein drawing?
Sure. So regarding the first question, honestly, we get a lot for free from GPT-4. Like, it has pretty good general understanding of both like similes and metaphors and more like pointed language. So, you know, we don't have a set of like super accurate benchmarks comparing like those two things specifically, you know, like similes versus more descriptive language, but it seems pretty good.
Okay.
And regarding the second question, that's another thing I want to explore in the future is basically generalizing this to more media types. You know, you mentioned protein drawing or sketches. You know, creative interactive graphics is just a really good use case for this because you just see visual output really quickly, but it could be pretty easily extended to, you know, it's generic enough that it can be useful for multiple other kinds of output. Thanks.
Hey, JD Zamfrescu, UC Berkeley. Super cool project, and I appreciated your talk. It was really great. So it seems like we're well underway, this transition to using LLMs to generate code and sort of make life easier, maybe both for programmers and for non-programmers, sort of anybody who wants to write code. I'm curious if you have thoughts on, you know, this initial step of ideas to code, merging sort of sketches, et cetera, together. Given all that, like, what are which are obviously very challenging activities before, like, what is the next set of challenging activities? Like, where has the bottleneck shifted to, you know, perhaps from like greenfield code to, well, I've got my initial set of code and I need to merge it. Like, what are the remaining sort of major bottlenecks, stumbling blocks that people ran into in the study?
Yeah, that could be a whole talk in itself. I think I would still say that this is honestly even too low level. I have a whole take on like agents and the future of coding and stuff, but I'd say that largely like the next, like the challenges will keep bubbling up like this, up like levels of abstraction until like basically the only thing that is challenging is how much you know about a particular problem or domain. Like, you know, in this case, the problem might be, you know, I want to make a fun sketch about San Francisco, right? And in that case, like, the main challenge eventually will just be like, how much vision do you have? You know, like, how good are your actual ideas, and like the actual implementation of getting there is handled for you, and ultimately you're kind of just like, you know, navigating concept space and like figuring out like, I'm basically just saying that the ultimate challenge will be how good your taste is, I think, and how well you can direct, you know, the little robots in front of you to, you know, fulfill your vision.
That makes sense. I guess I'm wondering if there are, we're not there yet, are there one or two things that you're observing now that are like the next bottleneck?
Oh, okay, yeah. I would probably say, I mean, this will be a problem regardless, but probably just like systems understanding. Like, I think a lot of coding assistant stuff that we see now is still like very granular and focused on like, you know, refactor this function or like look at this file or whatever. So the next steps of problems, like once basically junior engineering tasks are done, like the next step will be creating tools to help us understand like the system overall. You know, describing changes at a code base at a large level, I think.
Cool, thanks. I'll find you later, we can keep talking.
We can do one last question, but then we'll have to cut it off, sorry.
Yeah, thanks so much for an awesome talk. Really, really interesting, cool stuff. I was really curious about the semantic sliders and what kinds of program analysis you do to infer those semantic sliders and kind of determine that those are the particular knobs that end users are going to want to turn. And whether or not end users have a chance to correct those choices and say, actually, like, I want to turn a different knob. Yeah, curious about that.
Yeah, so I'm actually working on a re-implementation of that right now. But for the evaluation studies, basically what happened was that rather than extracting it after the fact, like somebody would enter in their prompt, and then before the code was generated, basically I had this function that would say, okay,
take out like key points or key phrases from the prompt and give me a set of global variables that you'll use in the sketch that you're about to write. And then that's just the mapping. And then it actually writes like a big comment at first in the generated code of the mapping, and then it uses that to generate. So there's a lot of kind of like pre-processing that happens afterwards, but that was basically the easiest way to guarantee that like, you know, the prompt and the sketch would actually match up. It's not like you just make the sketch and then figure out the connection afterwards.
Gotcha. Okay,
Yeah.
that's super interesting. Cool.
Yeah.
Thanks so much.
Just one quick note on that. If OpenAI actually released like the attention weights for like every token in a response, then I wouldn't have had to do that, because then I would be able to see like how the output actually relates to each token in the prompt, but they don't release that publicly. So, okay. Thank you.
All right, our last presentation is Color Field, developing professional vision by visualizing the effects of color filters. And it will be presented by Matthew Bedouin-Lufon. And their co-author, Jane E., is in the audience and is on the job market. So please reach out to them.
All right. Hey, everyone. My name is Matthew Bedouin-Lafont. This work was done in collaboration with Jane E., who you should absolutely hire, and also with Haijun Xia, my advisor. And it's about helping novices see color grading like experts. And so first, I'll define color grading as the stylistic manipulation of colors in photos or videos. So for example, here, the sky is made purple and the sunset a little bit more vibrant. But color grading is not like a niche hobby or anything. It's actually a critical part of any professional photo or video endeavor. Right? So everyone from your wedding photographers to your Hollywood directors have to worry about color grading at some point in the process. And so I'd like to start by asking you, how many of you have actually used a color filter, maybe on your phone, on Instagram, or something like that? It's a lot of hands. Okay. How about using something like Lightroom to edit photos and edit, the color temperature, things like that? Still a lot of hands. That makes sense, I guess. It's UIST. So how many of you have used a color grading studio complete with color calibrated monitors and hardware control surfaces? Okay, we have one hand. So evidently there's a huge range of tools that you can use to do color grading. And so a natural question then is, how does a novice who's interested in color grading go from selecting presets on their phone to using professional tools and becoming a professional color grading professional? So in ECI, I think we have a bunch of different approaches, right? If the tools are complicated, perhaps we can just develop strategies to help users learn the tools, right? Or maybe, we can make the task easier. We can rethink the user interface and maybe obviate some of the complicated control surface. But something that I think is often overlooked is actually just helping users understand the medium itself, right? So in this case, we're talking about color grading, and I think it's important because it's essential to the task. So it doesn't matter how smart your AI is, how good it is at generating color filters. At the end of the day, if you want to make decisions about color grading, you need to understand the domain. And only with that, you can actually do any iteration. And so if you're a novice, or a researcher, you might ask yourself, well, okay, so what's the target then? What does an expert do to understand their domain? And so to do this, in our paper, we turn to Chuck Goodwin's work on professional vision. So Chuck Goodwin is a social scientist, or was a social scientist, and in this paper, he studies archaeologists and lawyers, so very different populations. And he studies how they talk, and when they're working, when they're teaching, and when they're arguing. And what he finds are three interrelated discursive practices, ways of speaking. So the first is the use of a coding scheme, which is a fancy way of saying it's a vocabulary, they have certain jargon, and I like to think of it as a verbalized domain knowledge, to put that in sort of contrast with things like tacit knowledge, which are hard to talk about. So for example, in the context of photography, you may have heard of something like the rule of thirds, which is an abstract concept, which you can use in the context of a photo to make certain decisions. The second practice is highlighting. And really what that means is just drawing attention to parts of the image. So for example, if you want to talk about the vanishing points, you can just point at it. Or maybe you can draw on the image to show how it's coming to be. And so what's happening here really is that instead of looking at the whole image all at once, you can sort of take it apart in terms of individual components, look at sort of these details using the coding scheme. And then finally, we have the use of material representations. And these are just tools that experts use to apply the coding scheme in context. And I think this should be interesting to this audience, since here at UIST we like making tools. And this is an opportunity for us to contribute to these expert practices. So for example, in photography, you may have seen these composition grids, and what these are doing is that they're taking the concept of a rule of thirds and applying it to the tool you're making to take photos. And so when you're taking a photo, you can make decisions about whether you want to follow the rule of thirds or not, etc. So together, Goodwin refers to these as professional vision. And when you blur them together, really it's this idea that I think is quite intuitive, that experts cognitively enhance how they perceive their domain. Right? In other words, experts are able to just see more than novices. And this is something we see in color grading. Right? So here we have a filter that is sort of represented as a before and after image. And if you ask a novice to describe it, they'll talk about it kind of globally, and they'll say, overall what's happening. Whereas an expert will be able to say a lot more in a lot more detail. But what they're saying is, of course, not random. There's a structure to it. And that structure actually is the coding scheme. And so in this paper, we sort of focus on two aspects of the coding scheme for color grading. The first is the use of classes of color, and the second is actions on color spaces. So these classes of color are really just subsets of a color space. So for example, when you're saying that warm colors are getting saturated, instead of pointing at the subject or something in the background, you're pointing at colors themselves. And so you can talk about just the red and the yellows and the orange, and importantly, not talk about the blues and the greens. Which is exactly highlighting. The second one is actions in the color space. So if you're saying that the warm colors are getting more saturated, you're really talking about motion in this color space. So in this case, we're talking about motion along the saturation axis. And actually, what you're using here is the hue, saturation, and lightness color space, which we're using because it is what we call perceptually meaningful, which means that each axis actually means something in terms of how we perceive colors. And this actually matches the terms that people use and that experts use when they do color grading. So our goal then is to develop a tool that helps apply the coding scheme in context. And we're going to start with the notion of actions, and we're going to try to create a color filter that's, we're going to try to illustrate a color filter in terms of actions in a color space. And so to do that, we're going to start with thinking of color filters as functions. And so what we can do is we can take one of these the input of one of these colors, and we can plot it in the space just as a point, and then we can plot the output. And so together, that forms a vector. And because we're using a perceptually meaningful color space, you can look at each dimension of this vector, and that actually tells you something about how the filter is affecting the color. And it's telling you in the same way that an expert would say it. So for example, here, the motion on the left is saying that the color is getting desaturated. Vertical motion is saying that it's getting brighter. And then, here we don't have a lot of hue change. Now, looking at a single color is all well and good, but of course we want to see how the filter behaves in general. And so to do that, we can use a vector field. And so we can analyze that vector field kind of in the same way, where you can look at the overall motion and say that, oh yes, when things are moving upwards, this means that the image is getting brighter. And when things are gravitating towards the yellows, it means that the image is getting a little bit more yellow, which you can kind of see in the shirt here. And if you have a different color filter that makes things darker and blue, the vector field will have things gravitate in different directions. So we package this all in a user interface, which of course features the vector field, but also features the before and after image. So you're always talking about a color filter in terms of media that you actually care about. But we added a couple of extra features inspired by professional vision. So the first is the sample color, which you can select either from the image or from the vector field. And what it does is that instead of looking at all the filter all the time all at once, you can focus on very specific aspects. So it could be either one color, or you can scrub around and investigate how it's a certain area of the field is behaving. The second one is the ability to select color classes. Right? So since a color class is just a subset of the color space, and we have a representation of the color space, we can just highlight it in right there. And so what that does is that it both illustrates and contextualizes what that color class is. So for example, here with midtones, we can illustrate what midtones are as just the middle band of the vector field, or the color space rather. And we can contextualize it in terms of the media that you care about, so you actually know what counts as a midtone in real photos. So we conducted an exploratory user study in which we were interested in seeing how people would actually use this to analyze a color filter. And we talked to both novices and experts. I don't have time to go into the user study details or really the main findings, so I'll refer you to the paper for that. But I want to highlight two things in particular that we found interesting and surprising. The first is the connection between this tacit knowledge and more explicit knowledge, especially among experts. So here at the interview at the end of the user study, E4 says, when using Lightroom, it's just levers that you pull. You can kind of see what's going on with the output on the screen, but you don't get exposed to the internal mechanism like it is in color field. And so in the process of explaining, I realized I don't actually know what I'm talking about. I know the term, but to verbalize it to someone else is quite difficult. And so what's happening here is that because experts actually learn about color grading through using these parameters and just seeing what's happening on screen, they develop an intuitive understanding of how these are related. But that doesn't necessarily match with the sort of like stuff they learned in a textbook. And so something like color field can help by, by visualizing this code scheme, actually move some of the stuff that is in tacit knowledge into more explicit knowledge, which can help with things like communication. Another thing that was particularly surprising is the way we had our study set up, we had people describe a series of color filters, and so they would describe something with color fields, and then they went back to just using the before and after image. That just left the space right there. And one of the participants actually started using that space to talk about the vector field, even though it wasn't there. And so I have that as a clip.
Thing in like the bluish reddish range is pretty much going towards indigo. You can kind of tell that I'm like pretending like I'm looking at the color field right now.
And so, the fact that they're simulating the color field suggests that's like, either it's helpful to analyze a filter, or at the very least, it's helpful to talk about what the filter is doing. And either way, it's surprising that it turns into pointing an empty space. So I'll wrap up by saying that professional vision, in this case, we use color grading as a domain, but you can also apply it to a bunch of other domains. So we kind of touched on composition, and we'd actually use professional vision as a lens for some of this prior work. Or you can use it in very different domains, so things like audio engineering, where people or experts focus on specific areas of the audio spectrum and make decisions based off of that, which is the same kind of highlighting, but in a very different modality, which comes with interesting constraints and opportunities. So thank you for your attention, and we'll take your questions.
Hi, Jeremy Warner, Apple. So very interesting representation, and cool to think about just the space of it. So thank you for this talk. I'm also curious, outside of a visualization, do you think there's means for kind of using the color field as like an editing mechanism, or kind of a, not necessarily a replacement for those levers, but just like an augmentation or alternative to those tools?
Yeah, totally. So that's definitely one of the things that comes up. For this work, we didn't want to go into that direction because we're interested in the professional vision thing. But you can totally think about, what you're doing is, if you want to create a color filter, you're trying to create a vector field in this color space. And so you can imagine having things like brushes with feathering, so you can have like smooth motions in different directions. One of the challenges is that this sort of tool would be terrible for novices because it would be full of foot guns, right, where you can do things that like behave super weirdly. Yeah, there's a lot of different ways you can imagine doing that. But yeah, that's an interesting question. Thank you.
Thanks.
Hi, thank you so much for your talk. I'm Jenny from Stanford, and I love the way you've built on top of Goodwin. As you mentioned, professional vision is not just a cognitive framework for learning, right? It's a sociocultural one. You learn in communities, and all of these practices are not only shared in communities, but constructed together in these very socially situated ways. So I'm still left wondering what exciting things we can do in sort of the technologies for creativity or technologies for learning that keep humans kind of at the center, where we're learning or creating in social or collaborative ways.
Yeah, that's a really good question. It's also a little bit broad, but I think the strategy that we take in this paper is we started with kind of like a textbook and some of our own understanding as authors of color grading, and we sort of go off of there. And so these textbooks are also these socially culturally built things that you can go off of. But you can also just start talking to experts in how individual people sort of conceptualize things. Maybe you can build tools that sort of bring these different perspectives together, and so maybe you can sort of do things like that. I don't know. But no, I think that's an interesting question. And I think going from this perspective where you're looking at how people think about things and then trying to get other people to think in the same way is kind of the spirit that we're going for. Hopefully that answers things.
Yeah, sure. Thank you.
Thank you.
Thank you for the paper, really interesting. I think my question is about, I think we can talk about a process of professionalization as also a normative claim, right, about how people should be thinking and acting in a certain domain. And whatever tool you were going to build was going to make some kind of claim in that space. And I'm wondering how you are kind of thinking about that process, right? That you are kind of intervening into a social space where people get acclimatized to thinking in certain ways for certain reasons, right? Like in painting, like linear perspective is something that is like not kind of this like assumed baseline, right? But it's something that is like very hotly debated and contested of like, how do we want to think about this? Is this something that we think is kind of canon in our field or a good idea or not, right?
Yeah, that's a great question. Yeah, I mean, obviously this approach is by definition normative. You're looking at what the standard is and seeing if you can, better explain the standard. I think there's a fundamental difference in using that kind of as a perspective to understand the medium and versus maybe another approach would be to dictate how you actually create color filters, right? And so that's sort of like I think like kind of filter on that process where, giving information is very different from dictating from how people think about things. So obviously there's still an influence, but it's a different than the kind of influence that you might get from creating a tool that says like, oh, you should, have a suggestion like, oh, this is getting too red, like something like that, which be, I think, a lot more impactful in the normative way.
Yeah, absolutely. Thank you.
Thank you.
Yeah, we can take one last question before the lunch break.
I love this talk. It's so refreshing to see people tackling work at the space of like, we want to help people be better at doing these challenging creative things as opposed to we want to make challenging creative tasks trivial. So like, thank you for doing this work. So how a lot of the examples you gave apply to the space of either like visual applications or domains where we have established visualizations for understanding those. How might we think about using these techniques, if at all, for embodied expertise, where we don't necessarily have either like a visual space or an established way of presenting that knowledge in a visual format, like dance or sculpture or something like that?
Yeah, that's a really interesting question. Thank you. So I think there's a few approaches. So what I like about the audio engineering example is that you have to so experts will say things like, you can have this visualization for here like an EQ filter, right? And people will say, oh, if you're a novice, it's very tempting to make decisions based on what you're seeing with the visualization, but that is not the actual media. You have to be thinking about the audio itself. So there's a fundamental limitation in how we represent these things, which I think is a very interesting research question. I think in terms of like the embodied stuff, what it would go back to is like, what are the discursive practices, right? How are people talking about this? And, can we use that to make representations and sort of like start from that sort of like, just, the way people are talking. And, the way people talk is not like the full picture, it's missing the tacit knowledge, which is a particularly big deal for like the embodied stuff. But still, it's a good start.
Thank you.
Thank you.
All right, great. Thanks, everyone. So yeah, we have lunch now. And yeah, thanks for bearing with all the technical difficulties.
in the universe is something that we call in the universe is something that we in the universe is something that we call dark energy. Is something that we call dark energy. In the universe is something that we call dark energy.
there audio here? Is there audio out here?
Oh, on your, for like a video?
Yeah, but I will come back to the audio.
Yeah,
I guess not.
I think so.
You think so? It's not working, but
So the video's not playing?
it's playing, but without sound.
Sound is not coming out.
I guess it's done. Maybe that's it. Okay, sure. I guess I'm clear. Thank you.
Testing. Oh, it's on. Yeah, so we're going to get started. So everybody, welcome to the interface session on interface evolution, learning, adaptation, and customization. My name is Amanda Swearingen, and I work at Apple. And we have a bunch of exciting talks across various types of interfaces, including VR, desktop, mobile, etc. So just ask a lot of questions, hopefully, so I don't have to. And then, yeah, I hope you have a good final session for UIST. So for the first talk, we will have Towards Flexible and Robust User Interface Adaptations with Multiple Objectives by Christoph Younes, and he is looking for an internship for the summer, so next summer. So.
Yeah, we have had troubles with the HDMI before. I was told to try all the ports, so I guess we'll see. Do you think it's American thing again? Like last time it was this thing.
Yeah, it's showing it there, but it's not showing.
Yeah.
Do we have one on this side?
Yeah, there are two. One at least. What wizardry did you do last time?
We've got quite a few.
Yeah, you had this plugged in before.
Yeah, and it was working.
And it was working
Yeah.
before, of course.
Yeah. Yeah. I'll need the laptop.
Okay. I forgot which way.
I think it's just behind here.
Yeah, you just keep straight.
Yeah, I think it works fine.
Cool. Yeah, we're going to switch it around to Yifei is going to go first. So while we wait for Christoph's computer situation to work. And the paper is called Interaction Adapt, Interaction-Driven Workspace Adaptation in Situated Virtual Reality. So take it away.
Okay, can everyone hear me okay? Lovely. Okay, well, sorry about the technical difficulties, but so hello everyone, my name is Yifei Cheng. I'm a PhD student now at Carnegie Mellon University. Today I'll be presenting my work on Interaction Adapt, Interaction-Driven Workspace Adaptation for Situated Virtual Reality Environments. This was a work done in collaboration with Christoph Gebhardt and Christian Holtz while I was a visiting student at ETH Zurich. Our core contribution in this work is an optimization-based virtual reality adaptation approach that considers the interaction constraints and affordances of the user's physical environment. Virtual reality enables the creation of highly personalized immersive workspaces, but they're typically designed for a single environment. Work in reality, on the other hand, is increasingly situated in diverse contexts. For virtual reality devices, which are typically unaware of the environmental context, this introduces usability issues. Let's look at this through an example. Here I am working in my own personalized virtual reality environment. The layout currently works great in my own house. But when I move into an office, notice how the new physical constraints hinders my interactions. This is the problem that Interaction Adapt seeks to address. Given an understanding of the physical environment, Interaction Adapt automatically adjusts the placement of interface elements. It does so to support me in avoiding unintentional collisions, while also allowing me to take advantage of physical affordances within the environment, such as surfaces for passive haptic feedback and as a platform for rest. Interaction Adapt aims to build upon the growing body of work on interface adaptation techniques in extended reality within HCI. Prior approaches have explored a range of factors, including aspects relating to the user state, as well as the environment. All of these considerations can be thought of as building blocks of an adaptation approach. What prior work seems to not have considered yet, however, is how real-world constraints and affordances may either limit or support virtual interactions, and in turn, the optimal interface layout. Interaction Adapt proposes and explores this additional consideration. To explore how physical constraints and affordances impact interaction and how they should be accounted for in an adaptation approach, in a work we published at ISMAR in 2022, we investigated the human factors of interacting with surfaces in and around surfaces. Combining our findings with other empirical studies, we derived 4 core insights and interaction requirements. First, we found that aligning user interfaces with the physical surface enables significant benefits from passive haptic feedback. This entailed that our adaptation approach should prioritize the alignment of user interfaces with surfaces. Then we found that setting user interfaces to hover above surfaces can also be ergonomically beneficial. This enables me to take more restful interaction approaches, such as through anchoring my elbow on the table. As an implication of this, if user interfaces cannot be aligned with the surface, they should set to hover above them instead. Moreover, we found that direct interactions are faster and more accurate, so that they are preferable for productivity tasks. Therefore, in cases where the user interface can neither be aligned with the surface or set to hover above it, it should be placed to enable direct interactions. But direct interactions can also result in unintentional collisions and require significant physical exertion. In these cases, we want to encourage distant interactions instead. Interaction Adapt operationalizes these interaction requirements into an optimization procedure for adapting virtual interfaces. It takes as input a personalized virtual user layout and a pre-specified understanding of the target physical environment. The user-defined layout here more specifically refers to a set of virtual elements, characterized by their position, scale, and usage frequency. The target environment is characterized by a set of pre-specified surfaces, obstacles, and mid-air placement volumes around the user. Similar to prior work, we voxelized the given surface areas and placement volumes into smaller containers, and we treat adaptation as an optimal assignment problem. Interaction Adapt formulates this as a linear program with 3 objectives encapsulating the considerations of temporal consistency, occlusion avoidance, and interaction modality. Our main objective in this project is to model how the environment should serve as a constraint or affordance for interaction, and this is what I'll focus on for the rest of my talk. Recall our initial set of requirements. What we did effectively was model each requirement mathematically. For instance, to model on-surface touch interaction, we designed an objective term that highly scores assignments of elements to surface containers, especially within reach of the user. This is to support the touch interactions you see here. As an additional example, to prioritize UI placements above surfaces, we designed an objective term that highly scored assignments of elements to containers slightly above horizontal surfaces. This encouraged user interfaces to hover above the surface to support the elbow-rested interactions you see here. After modeling each interaction individually, our final interaction modality term combines and prioritizes these interactions in the order of on-surface touch, elbow-rested interaction, mid-air direct interaction, and distant interaction. Just as a recap of our approach in full, we combine our main interaction modality term with 2 terms drawn from prior literature. And by integrating all of these terms into an optimization procedure, our high-level objective is again to support interactions leveraging physical affordances. To evaluate our method, we conducted 2 studies. In our first study, we wanted to investigate the extent to which Interaction Adapt enabled ergonomic and efficient input. So we had participants perform a multi-window selection task with adapted layouts from Interaction Adapt and 2 baselines within 3 environments. In a second study, we sought to validate the applicability of Interaction Adapt to a real-world knowledge work task. We therefore had 12 participants again perform a travel planning task on adapted layouts from Interaction Adapt and a baseline within 3 environments. The collective results from our studies suggested that Interaction Adapt was indeed preferred over the baselines. And one of the core reasons for this is its alignment of user interfaces with surfaces and around surfaces. However, the studies also revealed that the approach is limited in its ability to accommodate for personal preferences, such as a strong preference for a fixed layout. This brings me to the limitations and future work of our approach. First, the environment understanding is currently done manually. Determining what an appropriate affordance is automatically would really benefit our work and offers an interesting direction for future research. Being able to accommodate for personal preferences currently also remains challenging, as we found with our evaluations. And this is another interesting avenue for future work. Lastly, we believe there's always value in expanding our toolbox of considerations in adaptive approaches. Some areas that are currently interesting and potentially underexplored are social factors as well as inter-element relationships. To conclude, if there's one thing for you to take away from this talk, it should be the idea that physical features within the user surroundings should be considered in the design of virtual reality workspaces for efficient and ergonomic input. And that concludes my talk. I'm happy to take questions.
Do you have any questions? I have one I can start.
Thank you. Hi, Judy Kong from University of Washington. Interesting talk. I wonder if you can elaborate a little bit on the last personal preference you mentioned. For example, what are the areas that people might have different preferences? Is more on the layout, the design, the sizing, or maybe the input and gestures, all of those? What are the different preferences?
I think one preference that really stood out was, if I put an interface somewhere, I expect it to be there again. And I think being able to perform adaptations in a way that could potentially benefit the interaction, but also take this into account is something that is remarkably challenging. And I think actually in Christoph's talk, they'll probably get into some additional approaches of addressing this. I think this is something we're still thinking a lot about, so I'd love to have this conversation afterwards. But that, I think right now, as of right now, I think the main kind of aspect of personalization I observed was to do with the layout placements.
Thank you.
Yep.
Hi, Yuan Lu from University of Notre Dame. This is really cool work. I wonder if you can speak more about the tasks that are associated with these interface design, different paradigms like mid-air or elbow-based. How does the tasks that you used in these different experiments affected your choices of the hierarchy for these different interaction paradigms?
I think that's a really interesting question. I think we made some assumptions about how people go about interacting with these interfaces. I think if you dig a bit deeper into the paper, we kind of characterize this in terms of just like a simple usage frequency parameter. I think it's hard. I think I completely agree with you in that, like, depending on how you interact with these interfaces, it should change, what would potentially be the preferable interaction approach. So currently, the tasks we assume primarily involve you basically touching individual touch targets, which is why if you look at the first task we did, that was kind of modeled on top of its law, and the second task, there was some scrolling involved, but I think currently we made the assumption that most of the interactions are tap-based. But there's a lot of nuance in this, and I acknowledge that as a limitation that we should kind of look into further as well. Yeah.
Sure, thanks.
Looks like that's all the questions, so let's move on to the next speaker. Yeah, so I'm happy to introduce Wei Hao Chen today, who is a fourth-year PhD student, and will be talking about From Gap to Synergy, Enhancing Contextual Understanding Through Human-Machine Collaboration in Personalized Systems.
Okay. Hi, everyone. I'm Wei Hao Chen from Tsinghua University. It's my pleasure to present my paper, From Gap to Synergy, Enhancing Contextual Understanding Through Human-Machine Collaboration in Personalized Systems. This work is done with my excellent collaborators at the PyLab at Tsinghua University. So, when we as humans communicate with each other, we leverage implicit information to convey, we leverage context information to convey implicit information, and this helps align our understandings. And we all want our communication with machines to be this context-aware, and this is where context-aware systems comes in. With the advancement of AI and IoT technologies, our intelligent systems have gained strong sensing capabilities. They can sense physical or social context to automate our daily use services. However, these context-aware applications face diverse user scenarios, devices, and preferences, and developers cannot predict every user scenario and make adjustments accordingly. Also, data-driven approaches also for sure in case of these sparse personalized data. So this is how we emphasize that end users should involve in this process. They should be involved to create their own personalized systems. And we have a popular paradigm, maybe some of you have known that this is the TAP paradigm, i.e. trigger action programming, where end users craft their own if-then rules. However, lots of end users report that they struggle to use this kind of system because, especially when they are unfamiliar with the device capabilities. The reason behind we discovered that there is a significant gap between human and machine of understanding how these contexts are constructed. We humans and machines perceive the environment differently, leading to the varying information we gather. And we use unclear concepts such as abstract or concrete concepts like vacation, lab, brainstorm, but these concepts, user-centric concepts overlap in meaning. However, machines use structured context representation. This leads to usability issues because end users may not easily make their unstructured needs into structured rules. So this is our work about. We aim to use natural language to simplify this process. Furthermore, we found that users have difficulties in effectively expressing their needs in natural language because they may be out of context, and they find it hard to fully describe the situation. So we propose an in situ collaboration of how end users can collaborate with machine assistants. We explore this process, use a formative study, which is a visual study. 6 participants participate, and they experience in simulated campus scenarios, and they communicate their contextual preferences to a human visitor, which was actually an expert in developing contextual system. They communicate via chat interface, and the visitor transforms the natural language into if-then rules that can be implemented on smartphones, and then communicate back using plain user-friendly natural language. We discovered that several challenges occur in this process. The first one is that user may use unclear terms, leading to ambiguity in context condition expressions. The second one is that users often leave out vital context information that should be necessary to construct machine Boolean expressions. The third one is that these participants actively seek out natural language explanations of these if-then rules, and the machine should also be equipped to explain their own limitations, like something they can't detect. The last finding is that the interfaces should allow users to, like, using user-centric concepts to control the expressions instead of intricate machine details. So this leads to our design of the Language Assistant, which is a context-aware dialogue assistant that allow end users to in situ construct their own personalized rules. Let me show you an example scenario, which is a user running in the playground and listen to music. However, he's interrupted by a notification, so he says, "Stop interrupting me, except for private messages." Our assistant leverages context information to understand his linguistic input and then replies with an contextual rule. This rule contains several shared contextual concepts. A concept is a pair of natural language phrase with its corresponding machine Boolean expression, and it serves as a medium for contextual understanding between human and machine. The user then converts further or select an appropriate SCC to communicate with this assistant until a satisfactory result was generated. Under the hood, we use large language model to generate these shared contextual concepts. Starting from low-level sensor data, we use expert development models to generate context descriptions of the current user. And then, along with these utterances, these descriptions are grounded on underlying detectors that machines can implement, and then expanded into potential Boolean expressions. Finally, these SCCs are combined and presented to the user. And this is a full video demo where the user is in a study room, accidentally switch audio from headphone to speaker and disturbs others.
In the universe is something that we call dark energy.
So you can see the other user was disturbed. So the user says mute if earphones disconnected to the language assistant. The assistant then replies with an interactive card containing several shared contextual concepts and natural language description of the rule. The user then further converses when others are wrong to add a new shared contextual concept. So you can see it's added, and he's satisfied with this generated rule, and then submitted his result. On the right part, this is a result contextual rule in JSON format we generated using Language. We evaluated language assistant in real-life scenarios and on Android smartphones. We also compared it with a baseline version, which only leverages user utterances without context information. 16 participants took part in, and the counterbalance, the order was counterbalanced. We collected acceptance of generated rules and their modification process with these two versions of existence. And we asked them to complete subjective ratings before, after each trial and post all trials. We ended with concluding interviews. Key findings are as follows. In terms of success rate, language significantly outperforms the baseline version, and this is a histogram of distributions of trials over the number of modifications. We can see that despite the baseline version have fewer modification number, but most of baseline modifications were made via natural language dialogues. However, language's modifications were mostly made via GUI-based clicks, which is easier. Participants also reported that they favor exploring possibilities with language because this version of assistant often suggested SACs that is beyond their expectations, and they found it useful later. Subjective ratings also show that users' preference for language. Among them are two key metrics. One is perceived machine understanding. That is users' perception of how the assistant can understand their intentions. Another one is enhanced understanding. This is an assessment of how users' understanding of machines' capabilities improved through the study, and these are significant. The last thing we found is that language also support a strong support for personalization. The first one is that different participants have distinct utterances to refer to the same thing, which is not very interesting. The other interesting thing is that different participants have different reasoning about context conditions, such as when not to disturb others. One may say, when I'm in a quiet place, another participant may say, when there are people around, so it shows different reasoning. The last thing is that different participants have personalized interpretation of the same concept, such as filtering important messages, depending on the relationship with the senders, reflecting their own personalized interpretation of importance. So to sum up, this is our work. We present language a collaborative approach for constructing personalized contexts, and we use large language models to generate shared contextual concepts. This bridges the human-machine context gap. I'm happy to answer questions. Thank you.
Any brave souls to ask a question?
Hi, David Lindelbauer, CMU. Very interesting work, thank you so much. So I was wondering, could you speak about, I didn't fully get, how does the baseline work? What did you compare against?
The baseline is also based on large language model, but it cuts the orange flow. It only uses user's utterance and converts that into detector phrase expressions. So it leaves out the in-situ context information detected by the sensors.
So you extract additional contextual information, add that in the second path.
Yeah.
Okay.
Yeah.
That's awesome. Could you talk about, while you only said LLM-driven, if you have any metrics of like how many errors does the approach produce? Like how good is the quality? Not just from like your user study, but also maybe from your personal experience. Does it make a lot of errors, and how well does it work just qualitatively?
Yeah. In our paper, we also reported the experts' ratings of the generated results of large language models, and it's we didn't have a percentage, but we feel that the results are qualified. But in my personal experience, it's like sometimes it may generate something that's is relevant to this context, but it's not necessary for me to use. It's a large language. ChatGPT may generate something like that. That's relevant to the thing, relevant to the situation, but it's not necessary for me to use in this contextual rule. It may generate something like that.
Hi, Anna Yu from Meta. I remember in the previous slide deck you mentioned you use LM to semantic connect all the sensor data.
Yeah.
Can you elaborate more on that? Does the LM generated sentence always make sense, or what technique did you use?
The most important part is the context description box you can see in the left part, because it can combine several detector results and generate a meaning of the current context because they are discrete sensing results, but it can generate a meaning. However, in the right part, we can see that we are using ChatGPT to generate Boolean expressions. It may cause some errors. So we use some code validation algorithms to correct that process. So in my opinion, the most important part is reconstruct context step that can generate a natural language explanation. That's the meaning of the current context. Yeah.
Thank you. We might follow up later.
Thank you.
Time for one more quick question.
Okay, I'll just make it quick. Thank you very much. Very interesting talk. I actually found the running example you showed a very interesting scenario because when people are running, it's actually very easy. You get out of breath, and sometimes I can't really speak complete sentences when I'm running. So I wonder in your the 12 scenarios you evaluated, was there any cases or any observations, potential failures of, when people have difficulty due to this context, have difficulty using natural language as the means to communicate with the agent?
The answer is yes. In some scenarios, participants found it hard to express their needs, such as when they are running, they are tired. So we observed that participants prefer later, out of the context, like 5 minutes or 10 minutes later, they recall this context and they refer to the experienced context that I want to establish a new rule. So that's an extension to this work, I think.
Thank you very much.
All right, let's thank him again.
Thank you.
So we have 2 speakers for this next presentation, and it's titled Learning Custom Experience Ontologies via Embedding-Based Feedback Loops, and it will be presented by Ollie Zaidi and Kelsey D'Urberville.
Thank you, Amanda. Companies and organizations rely on many different types of digital experience data to understand how people use their products. This data includes behavioral analytics, design data, and qualitative user feedback, collected with tools like Google Analytics, Qualtrics, and user testing. Rendering this data intelligible, however, requires significant manual work in the form of event tagging and filtering for analytics data, or recording, reviewing, and annotating user sessions for qualitative user feedback. These organizations use many different tools to collect and manage this data, and then often want to apply custom labels to it. A need-finding study we ran with analytics professionals revealed that custom language improves intelligibility and avoids confusion, but it is labor-intensive to set up and can require entire teams to manage. Dovetail, a transcription tool and qualitative research repository, lets users build a custom vocabulary to improve transcription quality. However, this vocabulary is not used beyond transcription. Tools like Amplitude may tag user interactions with generic language, but introducing custom language requires significant time and effort to instrument. Our system brings together click data and interactive design elements to understand semantically similar concepts and then automatically label other interactions related to that concept. It uses an initial vocabulary to label interactions with generic terms. When reviewing data, users can edit those terms to supply their own language. For instance, the system might initially label an interaction with the button Explore Our Parks with the term Browse, but the user might update it to View Parks. In the future, interactions with similar elements will be automatically labeled with the user's View Parks language by the system, whether or not the word park appears. Rather than memorizing the DOM element text, the system associates View Parks with the semantically similar concept Gardens to label that interaction as well. We built this system and we deployed it on usertesting.com, a platform that allows UX practitioners to recruit participants to test out their digital experiences. User testing records the behavioral and think aloud data from these participants and the design data from the digital asset. Practitioners then receive videos of the participants trying their digital experiences, transcripts and recordings of their Think Aloud data, and visualizations of the participant sessions. One of these is a SIGCHI visualization showing how a group of participants navigated a particular digital experience. This is where we deployed the feedback loop and custom ontology system. In this example, participants were attempting to book a pickleball court through the San Francisco Department of Parks and Recreation. We can see the path each user took and hover to check the screens that they visited. We can also see the interactions labeled with the starting vocabulary, terms like browse, get info, and read. Practitioners can then annotate each edge in the SIGCHI with their own language, describing the participant's intent. In this example, they update it with park-specific language. When updating automatically applied language, the practitioner can give the system feedback, telling it why they are choosing to do so. They can select too general, inaccurate, or other. Practitioners often perform tasks like competitive benchmarking, where they see how their digital asset compares to others in the same market. For instance, they may ask participants to do the same task, book a court, on, in this example, the Los Angeles Department of Parks and Recreation, a potential competitor to San Francisco. Here, participants are navigating the new competitor site, the LA Department of Parks and Rec, but attempting to do a similar activity, booking a court. So they're interacting with similar but not the same UI elements. The system predicts intent labels, both from the starting ontology language and the park-specific language that the practitioners used, annotating previous results.
Thanks, Kelsey. Yeah, now we're going to explain a little bit more about how the system works. We seed the system with a set of 71 common digital experience labels like browse, add to cart, and login. To bootstrap their vector representations, we leverage pre-trained word embeddings from existing language models. This enables nearest neighbor searches that return semantically similar concepts based on the text and design elements. For example, since the global intent browse is close to words like learn, explore, and see, if someone clicks on a button that says explore our parks, the system will return the intent browse. However, organizations may want to modify these global intents or add new labels to the intent vocabulary. So, the system allows, for example, the San Francisco Parks and Recreation Department to insert a new intent such as reserve, as well as replace the global intent browse with the custom intent view parks. The system adds these custom intents to the embedding space through a series of vector operations based on user feedback. Now, let's look at the feedback loop architecture at a high level. When a user interacts with an element, the element's text, along with the user's rationale, is passed to the feedback loop API. The system leverages this feedback to expand the intent ontology and customize the vector representation of terms through the use of vector space refinement functions. Then, when a user interacts with similar design elements in the future, the appropriate custom intent label will be surfaced through a nearest neighbor query over the embedding space. Let's dive deeper and look at how vector representations are computed for custom intents. Consider our example from before, where SF Parks and Recreation introduced a new custom intent view parks to replace browse. The goal here is to map interactions with element text such as explore our parks to view parks instead of browse. To accomplish this goal, the system creates a vector representation for the custom intent view parks by perturbing it from the global intent browse. Then, the vector representation for the element text explore our parks is attracted closer to the view parks vector such that in future predictions, when the system queries for the intent associated with explore our parks or other semantically related elements, the system will return view parks. This is just one of several cases in the embedding space refinement algorithm, so please refer to the paper for the complete description. In order to evaluate the feedback loop, we deployed it as part of user testing's platform, as Kelsey mentioned. Over the first 9 months of deployment, the feedback loop feature was used by 32 different organizations and companies in various market verticals like retail, transportation, healthcare, and software. We observed that the use of custom intents created by these users did actually surface in future tests, showing that the system was able to learn these new concepts from just a few user-provided examples. One thing that was interesting was that while users modified system-predicted labels, they rarely explained why they made the change. So the research team analyzed the custom intent changes and found that initial intent predictions were most often too general. There are several opportunities for future work. Currently, the system only considers a single interaction and text within design elements that the users interact with to predict intents. The feedback loop architecture is extensible, and future work should look to include multimodal inputs like visual features and screen layout data, as well as sequences of interactions. The feedback loop provides customization with respect to behavioral data, but digital experiences also include things like think aloud audio, survey responses, and even video recordings of people's faces. Future work can leverage our approach to build a comprehensive custom ontology for digital experiences. We also see a unique opportunity to build upon our work to better understand how organizations, teams, and individuals develop tagging ontologies in analytics applications. While we designed the proposed system for large organizations, it remains an open question of how much standardization should be encouraged and at what level of organizational granularity. Finally, this approach is a first step in generating actionable insights written in domain-specific language to help organizations improve digital experiences for their users. Thank you so much, and we can now take any questions, and please read the paper.
I have a question, actually, because I really thought this was super cool work. I want to hear more about like your experience deploying this like within your company, and if you faced any challenges in that process, you could share.
Yeah, I can speak to the start of it, just because this was stuff done while I was an intern at user testing, and I will say with deployment, it was something where it was definitely a challenge, and it was a pretty unique challenge because I feel like it was something where it's beyond just convincing yourself and the research team that this is something that we want to evaluate. It's convincing engineers and business professionals, and kind of the company sort of had to be invested in it. So it was extremely interesting and a really cool experience to kind of essentially show that this is something that would kind of help, I think, user testing, in its actual sort of day-to-day operations. And I think Kelsey can probably speak to a little bit more about where it is now.
Yeah, one thing I'd like to highlight here is that while I did reference the need finding study as part of this talk, that's only one of a lot of different user studies that we ran on this system, starting actually all the way back to building that initial ontology that in and of itself involved interviews with something like 15 to 25 UX professionals to develop that ontology, all the way through interaction design and then finally deployment. And I think that was probably a much more intensive process to get us actually production ready than a truly experimental only system.
Hi, Yuan Liu from University of Notre Dame. I actually was about to ask the question regarding multimodal representations, but you had that on the last slide. So I was actually curious, what are your thoughts on inferring intents using embeddings maybe of interaction traces in addition to individual elements that the user was interacting with? Do you think that's going to provide more context or information about the user intent?
Yeah, I definitely think so, because I think one of the kind of assumptions that our system sort of makes at the start is we kind of treat each individual interaction in sort of a vacuum and evaluate based solely on components on that individual screen. And even right now it's mainly text-based, so even just the first step is let's kind of look at the entire screen, where it's layout data as well as the visual data, the shape of icons, things like that. But yeah, I totally agree that I think not treating it in a vacuum and sort of going beyond that, the real kind of next step is that understanding that these interactions sort of happen and people navigate from screen to screen with maybe the same goal in mind, and it's not, okay, I'm just on the checkout page. It's sort of, there was a series of other pages they went through before they came to that, but it was all part of that sort of larger goal. So yes, I totally agree, and we're definitely kind of investigating that, and we look forward to, I think we're open to any sort of collaboration if people are interested in moving on to that next step. Thanks.
Well, yeah, let's thank the speakers again. And have the next speaker come up. Yeah, so I'll introduce the next speaker, and it's Jesh Soon. And the presentation is called Neighbor Environment Observer, an Intelligent Agent for Immersive Working Companionship. So really excited to hear more about it.
Sorry, maybe, yeah, this one. Yep. Hello, everyone. Could you hear me? Yeah, I'm Zhe Sun from Beijing Institute for General Artificial Intelligence. I'm glad to be here to share our latest work about interaction design in the context of living across the physical world and the virtual world. So these are my colleagues. And along with the rising trend of metaverse concept, more and more people start to think about using VR and AR devices in their daily lives. Companies keep updating their VR, AR head-mounted devices, including Quest, Apple, HTC Vive, Pico, and etc. There are also YouTubers trying to include VR devices as part of their lives by immersing in virtual worlds for days or even months. Now let's do a quick survey. Have you used VR devices before? Please raise your hands. Yeah, cool. And if you have been interrupted when using VR devices, let me see your hands. Oh yeah, so then you might agree with this. There are still many challenges for immersing in virtual worlds, especially for a long time. For example, it can be difficult for the users to notice external interruptions, such as door knocking or someone's calling, as the HMDs block their visual channel and reduce the audio channel. It is also harmful to the user's immersion for the user to handle those disruptions. You can see that the man just take a long time to notice that there's something calling at the door, and he has to take off the head-mounted devices eventually. And this one is for a ringing phone, and the man couldn't find the phone on the table until he take off the headset. So, and another perspective is the danger. For example, here, I should play it this way. Yeah, an example here, it can be inconvenient to grab physical objects when wearing head-mounted devices. As shown in the video, the man just spilled his coffee when he tries to grab it with the HMD on. So, in this work, we propose a method named Neighbor Environment Observer, abbreviated as NEO. With the help of NEO, things can become easier. It notices the visitor at the door and notifies the user by rendering a live stream in the virtual scene, which is, can you see my mouse? Which is on the right corner of the video. You can see that there's a small live stream here. And on the left corner, this is what's really happening at the door. So the user doesn't have to stand up, take off the headset, and go to the door to receive the visitor. The Neo just received the visitor with a tiny robot moving here, if you can see it. Anyway, there will be a bigger picture later. Yeah, so, and as for the ringing phone, Neo just pushed the phone to the user and render a virtual phone in the virtual scene so that the user could just grab it without having to take off the head-mounted device. And it can also consider a user's preference. If the user do not want to answer the phone, Neo won't help. So, I will then introduce this work from these 4 perspectives. Let's start from what is Neo. This figure shows how Neo exists both in the physical environment and the virtual environment. We denote the physical and virtual environment as the neighbor environments. That's why Neo's name from. With multiple sensors implemented in the physical environment, such as cameras and microphones, Neo collects environmental information as well as physical user information. As for the virtual side, Neo understands what is going on in the virtual scenes with access to multiple APIs. This table shows the 4 information categories collected by Neo, as well as their sources. We're trying to implement Neo with a minimal additional sensors. So most of the sensors are what the users already have. We only add additional cameras and microphones. Neo is designed to have the capability of helping humans to preserve their immersion when disruptions occurs. So the concept of Neo is to have something that lives across the virtuality and the reality so that the disruptions outside the VR scenes could be better taken care of. Then comes the question, why we designed Neo in this way? There was some work about creating smart assistants for professors, but they are not suitable for immersive working. And there are also researchers considering distractions by generating various feedback in VR scene that is corresponding to the distractions, and I really like this work. So what we are trying to do here is to deal with the problem from another perspective. Could we just help the user to handle them? We derived our concept of neighbor environment observation from symmetrical reality, where we model the virtual world and the physical world as symmetrical in terms of topology. So, how did we implement this concept? We built this system with 3 parts: observation, decision, and action. The 4 categories of information are observed individually and are transferred to the data manager before the decision manager. After an action is decided to be launched, the decision is transferred to 2 kinds of embodiments, physical one and virtual ones, through Wi-Fi. We format the past states using AND graph and convert them into occupation states. So what is occupation states? For example, here, regarding the user is in the middle of a VR meeting, while a disruption of coming visitor occurs, these 3 states are what the user is occupied with, and it requires these 2 states to be free to handle the disruption. So there comes the interferer. When this happens, Neo has an initial probability to take action. However, this probability will change after every round of personalization by questionnaire. You can see the yellow point M here. This is where the initial probability is, and it changes from this point. If the user dislikes this action of Neo, the probability goes 1 step to the left. If it still dislikes, it goes 1 more step to the left until it reaches the lower bound. Otherwise, it will go right until it reaches the upper bound, so that the probability of taking action will change according to user's preference. That is how we do the personalization. Oh, by the way, the function is sigmoid function here. So, and as for how do we actually take action, we do 2 kinds of implementations in both the physical world and the virtual world. In the physical world, we developed a desktop robot system with a tray and marker and speaker on it, so that it could move things in the physical world for the user or go to the door to receive visitor. As for the virtual implementation, we build up a simulated virtual scene for VR meeting, and we generate various kinds of feedbacks in the virtual scene for a better user experience. And we did 3 kinds of experiments to test our system. There are 2 system experiments and 1 user study. As for the system experiments, we designed several kinds of occupation and disruption, and we activated different group of sensors in the system to test why should we use the sensors from both the physical world and the virtual world. So the result shows that the accuracy is reach the highest part until we activate both sensors from the virtual world and the physical world. The second system experiment lays on the personalities of the personalization. So we simulated 3 kinds of users. One is always annoyed by Neo's action, one is always satisfied, and the other one change its mind in the middle. And we could see that the action probability actually change along with users' preference. So we could say that the personalization period is working. And as for the user study, we recruited 12 participants with VR experience and work online frequently. And they are asked to experience a experiment of 3 phases, which is control phases where no assistance was provided, and O-Neo phase, which is original Neo phase, where the Neo with original probability helps the user to handle the disruptions. And P-Neo phase stands for the personalized Neo. The results shows 4 kinds of conclusions. One is Neo could, whether the O-Neo or the personalized Neo could give better engagement, and it could also lower the workload according to the NASA task load questionnaire. And it could make user experience a little bit higher, especially in the pragmatic quality channel. And the last, it could provide a higher satisfaction after the personalization. So that's all for this talk, and thank you all for listening. I'm willing to the questions.
It's time for one quick question, if anybody has anything. What do you think you would do next? Like, what other sensors would you add to this?
Oh, yeah, of course. Thank you for asking that. Currently, we are using only cameras, microphones, and those APIs from virtual scenes. And we are thinking about adding more sensors about the perception of the environment, such as the air condition, or the use IR cameras to detect things are moving or whatever, so that we could have more disruptions detected for Neo. And second, we are going to improve the decision module, which is what I am now doing, and the work has been submitted to another conference about AI. We are now using a simple model based on the probability. So we are trying to use AI here to make the decision of Neo more smart, intelligent, and suitable for users' need.
All right, thanks again.
Thank you.
Yeah, thank you so much. So our next speaker is Jason Wu, and he's a PhD student at Carnegie Mellon and also intern at Apple, and is presenting work on never-ending learning of user interfaces, and he'll be going on the job market too, so he comes with the highest recommendation. Although selfishly, I want to keep working with him, so yeah.
Thanks, Amanda, for that introduction. Okay. All right, hello everyone. I'm Jason Wu, and it's great to be here to present the Never-Ending Learning of User Interfaces project. And this project is something that I did with my collaborators at Apple, Rebecca, Eldon, Amanda, Jeff Bigham, and Jeff Nichols. So now, more than ever, there's been a growing interest in how machines or agents can robustly understand and operate user interfaces. And there are a lot of things that they need to know in order to do this. So these are things like, hey, what are the UI controls on a screen? How are these controls arranged to display information or functionality? And finally, well, what can I actually do with this UI? Or in other words, what are its affordances? And a lot of research has gone into building data-driven models to answer these questions. And this has led to great systems for accessibility repair, task automation, and design tools. But right now, we as humans, we have to teach the machines how to do these things by providing tens or even hundreds of thousands of annotated UI examples. And as you might imagine, this process is really time-consuming and expensive. Widely used data sets currently out there has been estimated to cost tens of thousands of dollars to collect and is several months of human labor. So this makes it prohibitively costly to continuously update the data sets to include the newest versions of apps. And this is really important because UI designs change all the time between apps and even OS versions. And finally, human annotation is surprisingly error-prone for a lot of UI semantics. Previous work has shown, for example, that if you ask human annotators to annotate which elements are tappable from a screenshot, this actually leads to really high rates of disagreement because of ambiguous visual signifiers. So to give an example of this, I wonder if you can guess all of the interactions supported by these UIs here. So some are more obvious than others, right? So we can probably guess that, hey, we can tap on this toggle here to toggle it, and we can also tap on this change button. But in fact, there are many more. So for example, we can actually drag these list items to delete them. And actually, depending on where we tap on them, different things will happen. So we made some observations here, right? First is that it's just difficult to annotate user interfaces at the training stage if we only have these screenshots. And more importantly, right, as a human, we don't need to learn from annotated examples, right? And a lot of times we actually eventually learn how to use apps by just playing around with them and discovering functionality. And so the question is, well, how can we get machines to do the same thing? So towards the first goal of going beyond screenshot annotation, we designed some labeling heuristics that basically take segmented video clips or screenshot sequences and infer effects of interactions. So for example, we can start with an initial screen, then if we want to learn about one of the elements, we can simulate a tap on it, right? And if the post-interaction screen is a new screen or has some other kind of visual change, then we can infer that that was most likely tappable. And this is just another example, right, for draggability. And what we expect basically is if the element is draggable, it can kind of like follow our finger. So that's a heuristic for draggability. And towards the second goal of learning more like a human and discovering things over time, there's actually this framework in the machine learning literature called never-ending learning. And this is interesting as there are four kind of main goals in this framework. As the name suggests, of course, right, the main thing here is that we want to be able to learn over prolonged or potentially even unlimited periods of time in a self-supervised way. And another thing this framework gets us to think about is strategies to kind of use previous knowledge to help with further learning and also avoiding model performance stagnation. So we use these four goals as kind of, we use these four goals to guide how we implemented our system and also how we ended up evaluating it. So we built the never-ending UI learner, and it's a distributed crawler that automatically installs real-world apps from the App Store and crawls them. And from a high level, right, it has this, it gets a lot of real devices, installs real apps to them, and then continuously crawls them by attempting various interactions using either a random policy or a policy that's actually driven by model confidence. And using these observations from the interaction, we're actually able to generate labels. These labels are then sent back to a central server, and they're used to update these models, these UI semantic models. And these new models are actually pushed back into the crawler itself, so it affects the behavior of subsequent crawls. Each crawler is equipped with some machine learning models that predict UI semantics, and we actually designed some new architectures for this that was more efficient for this style of online learning. The key here is that we basically tried to minimize the number of trainable parameters by adopting what's called a multi-headed architecture, and this is basically desirable because it improves learning efficiency and also stability. To give you an idea of how, To give you an idea of how all this works together, here's some footage that we saved from our crawler running on some apps, and we can see in this sped up footage that it's basically attempting to tap and scroll and drag elements to learn what's on a single UI, but more than that, it's actually exploring to new parts of the app to get more training data, examples for itself. Okay, so how well did this work? We conducted a series of experiments where we ran our crawler on for 5,000 device hours, where it performed over 500,000 actions on 6,000 real apps. And our primary question was, well, how well does the system perform over time, right? This is a never-ending learning system. And one of the other goals I mentioned earlier for never-ending learning was that we want to look at strategies to reduce model stagnation. So we wanted to investigate some of these different crawling policies. And so it's important to also know for these experiments, we basically validated them on a held-out set of apps where we asked human annotators to annotate recorded videos of those apps, and as opposed to screenshots. So we used our crawler to train 3 models in total. I showed you the first 2 affordance prediction models, and a third is something called a screen similarity model, which basically tells us if the crawler arrived at a new screen, which is helpful for some of those heuristics that I showed you earlier. But actually, this model itself is improved over time as well. And each crawl epoch on the x-axis here basically represents installing each of the 6,000 apps once, and it's actually reinstalled every epoch because it can actually change in the meantime. And you can see the crawler learned the tappability and draggability models completely from scratch without any human labels, and actually continues to improve over time. And for the screen similarity model, again, we started from a pre-trained model from existing work, and we were able to improve that. And for the crawling policies, we tested we tested one policy that was randomly selecting an element to learn about, and there's some variations of a technique called uncertainty sampling, where we can select samples based on low model confidence, for example. And in our experiments, the simple random policies seem to perform the best, but I think there are probably some parameters that we can tune for the uncertainty sampling. What we noticed so far is that if the model always chooses the same types of low confidence samples, it could lead to a little bit overfitting in the next batch. Okay, so to wrap up, our work is motivated by the interactive nature of user interfaces and using that to the advantage of machine learning-based UI understanding. We applied the framework of never-ending learning to user interfaces to let machines use and learn to use UIs more like humans do. And we implemented our system and let it, run for 500,000 actions on 6,000 real-world apps, and the resulting models learned from these interactions are more accurate than ones that you could get from human annotated screenshots. And thank you. I'm open for questions.
Hi, Judy Kong from University of Washington. Really interesting work, and I love this talk. Thank you so much. I really like the idea of using the video clip and see how it changes. after this crawler's action. So I wonder, how do you differentiate, let's say if there is a GIF or some animation inside an app, whenever you see that visual change, how does this model differentiate between, or how does this model understand whether this is caused by the crawler's action or it is some kind of non-significant visual change?
Right, that's a great question. So that's a detail I kind of skipped over a little bit briefly, but in the heuristics for these labeling, interaction labeling, we actually establish a baseline. So there's actually multiple screenshots taken there. So if there was a GIF, right, we can know like which regions of the screen are changing before the interaction happened, and we can kind of use that to rule out some of those false positives.
Thank you so much.
Yeah, thanks.
Hey, great talk. One quick question is that for drag, especially like sometimes super weird. For example, one of the example app you showed there is like the Tips app in iPhone, and the Tips app, if you drag a little bit towards the left and right, it will change the screen, so it shows that it's scrollable, but it doesn't necessarily navigate to the next screen, right? So you have to drag for long enough, and it would snap to the next screen. So, like in your system, do you have like a long drag, short drag? Like how do you distinguish between them?
Right, that's a great question. So yeah, actually it turns out depending on how much you drag, different things can happen too. Our heuristic, I think we had a set ratio that was basically like a ratio of the actual element size. I think it could be pretty easy to extend this. Like we can have like a multiple heuristics attempting like different levels of drags, right? So that's not something we tested in this particular version. But yeah, like I think for a lot of the drags, it was basically like half of the element width, and that was enough to detect.
And then you basically observe, for most of the cases, that will trigger, if it will actually have an element change, it will trigger element change.
Trigger an animation, sorry?
Like a navigation. So when it is
so the drag doesn't necessarily result in navigation. It'll just follow your finger. The tapping one, it might trigger navigation, like the dragging.
And then when, for example, in setting as if you drag down a little bit, you don't consider that to be a navigation.
Oh, like a scroll?
Scroll, yeah.
Yeah, we also count, we have vertical dragging, which is basically scrolling potentially, and also horizontal dragging, which is like the dismissing. Those are kind of separate heuristics. Yeah.
Cool. Thanks.
Thanks, Jackie.
Maybe just one quick, and then you're gonna come up.
Okay. James Egan, Institut Polytechnique de Paris. Have you considered, it looks like you're using just screenshots, so the surface representation. Have you thought about extending this with deeper, for example, you have access to the Windows server stacking levels. Have you considered extending some of the training model to take that into consideration?
Right, so if I understand correctly, you're asking like, what about like the metadata maybe of apps?
Right.
Right,
but
so that's a great
metadata in just the way that the the various UI components are stacked on top to draw the screen.
Right, kind of rendering information. Yeah, so that's a great question. This is actually a huge theme in accessibility where that information can be really useful, but it's also not always available, and that's also one of the reasons why a lot of apps are not accessible to screen readers. So in our particular work, we're kind of focusing on like pixel inputs, and it's also kind of useful for like at the design stage where you might not have something that's literally rendered yet. We're just drawing things. So it could be useful, but it also might not work for some use cases. So that's why we looked at this.
Thank you.
Thank you, Jason. I'd like to introduce our next speaker, Jae-Shan Chen from Zero. And this paper is called Unveiling the Tricks, Automated Detection of Dark Patterns in Mobile Applications. So.
Hello everyone, my name is Jae-Shan Chen from CSIRO, and this is the collaboration work with the Monash University. So the paper title is Unveiling the Tricks, Automated Detection of Dark Pattern in the Mobile Application. So what is a dark pattern or the deceptive patterns? You may not be familiar with this term, but it's actually everywhere in our daily lives. They are there in the home IoT device like the Apple TV, and they are also there while you're watching the video like in the YouTube video. And they're also actually everywhere in your mobile application. So here's some example there. For example, for the first example, this is a pop-up advertisement that suddenly pops up and interrupts your current task. And you may also see those disguised advertisements that mix themselves in the normal contents of the mobile application, and sometimes you just accidentally click them, and this is not what you want. And while those annoying experience you may have, you also sometimes may encounter some financial loss. For example, the last example, there's a false continuity. The apps provide you some free trial before you actually subscribe to them. But what you may not, you may find surprised that after the free trial, you suddenly someday find your bank account is being charged because they hide the small text under the screen that show you will automatically opt you in after the free trial. So they are actually quite prevalent according to the existing research. As you can see, there are 95% of the mobile application contains at least on average 5 dark patterns in their user interface, and the 11.1 shopping website also contains certain kinds of deceptive patterns. So let's officially define what are deceptive patterns. They are an user interface that maliciously crafted to deceive the users into performing action that may not of their best interest. There are actually many legislative action. For example, the California Privacy Rights Act and the European Data Protection Order Board, they try to publish some guidelines on constraining the uses of the deceptive patterns. There are also many academic efforts on this. For example, some researchers try to explore the user interface in the mobile application and summarize a taxonomy for the deceptive pattern from different aspects. For example, the website, mobile application, IoT device. And there are also some people that provide a crowdsourcing platform for the end user to post their deceptive pattern they meet in their daily life so that they can name and share the company that use those patterns. And there are also some development patch that try to use certain patch to cover those user interface by something like reverse engineering techniques. But all of these methods require some many manual effort, and some of them also require some heavy expertise, like the programming experience, and it is hard to generalize or it's quite time-consuming. So we are thinking maybe we can propose some method that can be more lightweighted. So as the advantage of the computer vision technique and the pattern matching, so we are thinking about maybe we just propose a lightweight tool that leverage the advantage of those existing technique and then to detect those patterns automatically. So here's our tool called UI Guard. So basically, given a user interface screenshot, we first extract the key properties that are quite important to the detection, and then go through our knowledge-driven dark pattern checkers. After that, we can output the if there are any exist of the dark pattern, we will show the position and what they are. So as seen in this screenshot, it actually contains 2 kinds of dark pattern. The first one is a pop-up advertisement, which I mentioned before, and another one is the false hierarchy, as you can see on the bottom of the right image. The install option is actually more salient than the no thanks button. So the user may just click on the install button because they may not see the no thanks action. So why we detect those properties, for example, the element coordinates or element types, and how we distill the knowledge to check the existence of a dark pattern. So basically, as there are many existing taxonomy on the academic papers, so we try to integrate them into a unified one, and which we obtain around 5 primary categories and 27 cases. And then on the right side, there are some detailed description of those cases, and then we conduct a characteristic analysis on these patterns, and we recognize there are six properties that are quite important for detecting those patterns. For example, the element types, they are coordinates, text content, or the status, icon semantic, colors, or some relationship between those elements. So here is the knowledge we obtained, some heuristic rules about how to detect those dark pattern based on the property we extract. For example, for the pop-up advertisement, we need to first check whether it is an advertisement, and then check whether the style are similar to other elements in the current UI. So after we develop our system, we want to know if our system is actually good or not. So we conduct an accuracy evaluation. As there are no existing data set on the dark pattern, so we basically manually annotate around 6,000 user interface from the UICode data sets, and which yields 1,600 dark pattern instance. And in terms of the classifying whether the user interface is a deceptive pattern or not, our tool achieved around 85% in the accuracies. And then in terms of what kind of dark pattern it is and where it is, our tools also achieve 82% in the F1 score. We also conduct a user study to evaluate the usefulness of our tool. So we invite around 58 participants from various backgrounds. Basically, we just first provide the definition of a deceptive pattern and ask them to evaluate the user interface based on their understanding. And after that, we have an education session, like we show the result of our UI guard and to let them know the difference between their detection result and ours. And after that, we ask them to evaluate another similar set of user interface and try to compare is there anything changed. So here shows the result. Before the education, the participant can only recognize around 18% of the deceptive patterns in the experience user interface. But after the education, the record rate increased to 57%. And the majority of the participants think this tool is very helpful, and they want to know when we actually turn it into a product they can use. So in terms of the application, our tool can actually help different stakeholders. For example, the regulators, for example, like I mentioned before, the California, the European has adopted some guideline on constraining the uses of dark pattern. So by using our tool, we can generate certain deceptive pattern report so they can reduce the manual effort, because there are so many millions, thousands of the applications on the market right now, and they keep growing. And another regulators would be the app market. If they would like to take the responsibility to also help with the constraints, it will be quite helpful, because all the applications nowadays need to go through the app market so that people can install them. And another one is for the end user. Our tool can also be used while the end user using their mobile application, and we can highlight the potential issue on the current screenshot so that during this process, they can learn the knowledge of dark pattern during the time and then recognize them by themselves later. And the last one, we also want to help the app provider with the detection of the dark pattern in their own application, where they may be the one who intentionally to create those patterns. Maybe by showing the existence of dark pattern in their user interface and also showing the potential law they break, it may help them to revise their design. So in summary, today I introduced the concept of the deceptive patterns and show the system structure of our UI guard, and we also conduct a user study to evaluate the usefulness of our tool. And our work can benefit 3 different stakeholders. That's the end of my talk. Thanks for listening, and I'm happy to answer any question.
Thank you so much. Really cool.
Hi, Yuan Lu from University of Notre Dame. This is really cool work. I just want to clarify on the system architecture part. I might have missed it, but can you tell me more about the input of the checker and like what kind of information and the modalities that you provide for the checker?
Okay, basically we just, because our input is just a UI screenshot, as the view hierarchy may have some issues, for example, incorrect location for the widgets or fail to capture the elements on the screenshot. So we only focus on the visual information on the screenshot. It's the same as how people perceive the user interface while they're using the mobile application. So the modality, the input is user interface with a visual, is an image, but we extract the information as a textual format. And so the property is in the textual format, and we only examine the textual information to see if match with certain rule.
Okay, quick question. Any plan to open source this?
Yeah. I plan to open source it maybe at the end of this year.
Okay, sounds good. Thank you.
Okay, hi. Hello, Jishan. Hello. Yeah, thank you for a great talk. A little biased by my own talk. I was wondering if you ever thought of like a dark pattern that requires you to use it over time to see that it is a dark pattern, because the Wall Street Journal example, right? Like you only know, maybe it's clear that it's a dark pattern when it starts to charge you money after like a month, right? So I was wondering if you knew like of some dark pattern that is harder to detect at a single screenshot level.
Yeah, that's actually a great question. So I didn't mention before. So basically, after we conduct the characteristic of the existing taxonomies, we find that we can actually categorize the dark pattern into two categories. The first one is the static user interface dark pattern, which only involves a single UI. Another one is a dynamic dark pattern, which involves a multiple user interface. And actually, our current works only focus on a single user interface. And the multiple, the dark pattern related to the multiple UI will be our future work.
Okay, thank you.
Thank you.
Cool.
Okay.
Yeah, I think we're kind of out of time.
Oh, okay, fine.
Yeah, you can follow up afterwards. Yeah, so we're going to have one more, actually a little out of order. So Christoph is back. The talk is towards flexible and robust user interface adaptations with multiple objectives. So excited to finally see it.
Yeah, me too. So in light of Halloween, this talk seems to be cursed, so that's nice. But we'll get through it, and I appreciate you sticking around for it. Okay, so I'll be presenting towards flexible and robust user interface adaptations with multiple objectives, which is the product of a collaboration between Aarhus University in Denmark and University of Saarland in Germany, between me, Christoph Jons, João Bello, Anna Maria Veit, Clemens Glockmose, and Ken Pfeiffer. So I had this brief primer about adaptive user interfaces planned here. That would have worked if I were the first presentation of this session. Now you've seen adaptive interfaces, there are a bunch of posters out there, so at this point, maybe just a quick reminder, it's, well, 3D things. If I walk from one room to the next, how does my virtual content react to that change? It's 2D things, colors of chat applications. It's menu layouts that adapt to these patterns of usage. So all these things kind of live in this adaptive UI realm. How I like to think about them is you have a bunch of these potential adaptations, potential changes to make to UI in order to respond to a change in the current usage context. And you have some kind of filter, some kind of adaptation model that captures your design goals, what's good about an adaptation, captures the user preferences, and somehow shrinks that down to one or a few adaptations, actual changes to the UI to present to the user. And this adaptation model, that should take into account this notion of context. So things like lighting conditions, user pose, emotional state, all this lives in this context node. There are many ways to achieve this. You can have rule-based systems that rely on heuristics, you have prediction. We are dealing here with this class of optimization-based adaptive user interfaces that use, well, optimization to achieve these adaptations, to act as this filter. And specifically, we're going to be dealing with this problem of underspecification or uncertainty in context. Basically, what this means is you have a lack of information about what's going on around the user, about this context. So this could be things like the preferences, this model of the user's preferences aren't perfectly captured in your system, or maybe there's a relevant contextual dimension that you forgot to include in your model, or quite simply, it could be imperfect sensors. Maybe you get some noisy signal that's not quite where you want it to be. So we propose a change to this optimization problem formulation in order to better deal with this uncertainty in the notion of context. And we'll see about its implications shortly. So let's look at a concrete example that's also in the paper. Here, this is 3D UI adaptations, so very similar to what Ife showed, actually, in a sense. This is an architect's office that you can imagine in this kind of 3D mixed reality setting. So you see this cluttered office desk. There's a bunch of office supplies on there. You see the sticky board thing in the back. There's also a floating chat application to the right, kind of modeled after iMessage or WhatsApp or something like that. And there's a blue plan of a building that this architect is currently working on, lying on the desk. The architect wants to review a 3D model of the current building, this housing project that they're building. So where should we put it in the scene? Well, maybe we want to put it in close proximity to this blueprint. After all, they're semantically connected, right? But maybe the center of the field of view is another good guess. After all, it's easy to see, easy to reach. Or maybe it's the architect's intention to rather glance at it. So if they're left-hand dominant, maybe you want to put it to the left. If they're right-hand dominant, maybe you want to put it to the right. The point is, there are many potential positions for this house that could potentially be preferred, and we are lacking the information to clearly make a decision. Usually, how these adaptive user interfaces work is they make a best guess. They pick one of these according to what this optimization problem spat out, and they put this solution there as sort of the thing to deal with. We propose to this change in the optimization problem that instead of just a single proposal, we give these varied set of, well, sort of affordances or suggestions to the user to pick from, and then correct as they see fit, with the idea that they know the context best, so there's not only one close to the blueprint, but also to these other positions that might be relevant. So how is this achieved? Well, to answer that, you have to go back to this notion of the adaptation model. In most current systems, there's this weighted sum optimization, this term that captures a set of objective functions that express how good or bad a change to the UI is, that is then weighted with some terms and minimized if it's a notion of cost or maximized if it's a notion of utility. That has many benefits. It's simple, not only to understand, but also to optimize. You get some controls over this adaptive behavior via these weights. And on a more neutral note, maybe, it gives this single immediate adaptation, which can be a good thing. However, you have to deal with this problem of how best to set these weights to get the behavior that you want to achieve. And this is more like a technical note, this problem formulation can only deal with this certain class of optimization problems where the Pareto frontier, the objectives, form this convex shape. So instead of this, we propose going to a vectorized multi-objective formulation that instead of giving a single adaptation proposal gives this set of proposals that we've just seen. So you get the benefits of no weight tuning necessary. There are no weights in this problem formulation. You can optimize for any Pareto frontier shape, not just the ones on the convex ones, but all that are potentially preferred according to this Pareto optimality. But you get the problem of how do you select the final adaptation to present. And for that we say, as long as one of the proposals you give to the user is close, they can select it and correct it as they see fit. So let's look at that briefly in a live system. Here we have this mixed reality setting again, where the user launches via tap on the wrist these adaptation proposals. They show up in their environment, and they can then select one, in this case to display a browser with some UIST conference details, where they see fit, and correct it as they need it. In the paper, we take both a qualitative and a quantitative look at this, but here I just want to briefly focus on this quantitative look. We conduct a simulation-based evaluation where we have a simulated population of, a population of simulated users whose preferences can be perfectly controlled. And then we compare both the dominant optimization method of the weighted sum and our vectorized multi-objective optimization formulation.
in terms of both the time it takes in order to generate these proposals and their quality in terms of maximum utility. Just a quick side note here, these preferences are captured as weighted sums in order to make it most beneficial to the current state of the art and most challenging for our proposal, and include things like ergonomic objectives or semantic objectives. Just a few highlights here. In terms of adaptation speed, this vectorized formulation scales well even to many proposals, versus the weighted sum that needs to be run repeatedly in order to generate these suggestions. In terms of robustness or quality, giving these set of proposals gives flexible options that are robust to even challenging Pareto frontier shapes like the concave Pareto frontier shape we see here. So, quick look ahead. Since we focused on this more simulation-based evaluation, it is yet unclear what this effect of these multiple proposals is going to be on both perceived user control and on cognitive load. And similarly, since we focused on this 3D UI layout adaptation domain, it is unclear how these results would then generalize or translate to other adaptation domains, maybe ones that are less visual, like timing of notifications or menu adaptations. Taking this one step higher, even though this does not require any additional information, we still need to align this optimization problem with users' preferences. So how best to do that remains an open question. And finally, sort of taking it all the way up, this paper dealt with this problem of uncertainty or underspecification of the context. That is a huge problem, a huge topic that this is not the silver bullet for. So we will continue working on this, and we invite you to join us in that effort. Thank you.
Sorry, thank you for the great presentation. One other question is that if we are looking at the larger space, so providing multiple options to the users might be sort of made them indecisive or would be obtrusive sometimes. Have you considered that case, that when is a good time to actually provide many options to the users? Or,
yeah, excellent question. So there are many parts to this. One is this large space of potential adaptations, and one is sort of the question of when to present and how many of these proposals to present. So in terms of how many to present, I think that really depends on the kind of situation and the system that you're looking at, and the situations that you want to apply it to. So we were looking at small-ish sets of these proposals, but I think if you switch your thinking about these adaptive systems as maybe recommender systems or more closer to recommender systems, you get a feeling for what kind of recommendations and suggestions, including how many, make sense. But there's a large entanglement with the presentation technique of this as well, so it's not yet clear how that is going to play out. And in terms of when, I think this works really well for these sort of stationary or semi-stationary scenarios where you go from one task or one stage to the next and not are constantly dynamically moving. So it makes sense for you to get some assistance in setting up your environment for that situation because you're going to spend some time in it. But it's not this constant change where you're constantly checking things from these suggestions.
Do you think your approach could be combined with like Yifei's approach for making an even better UI adaptation system?
So I think there's many parts of Yifei's kind of work that complement this and ones that maybe brush up against it a little bit more. So in terms of the objectives that are in there, I think having this large set of objectives works well as long as you still ensure variety in the suggestions that you can give. So as long as you retain, and this is maybe a bit of a technical term, a broad Pareto frontier that spans many meaningful options, so as long as you have many meaningful optimal suggestions to make, then it works well. But if you have objectives that basically just target one or a very, very small set of semantically very similar suggestions, which can happen if you keep including more objectives, then it may be more tricky, and you might need another way to give this variety to users.
Hey, Cheng, we're working on it, Amanda. We'll get it done at some point and combine our work. So you mentioned there's a challenge with weights. What about the functions? So I guess, in a lot of the work we see some sort of exploration of individual considerations. This seems like a potential framework to combine everything and see, what actually matters, what doesn't. Can you speak a bit to that?
Yeah, I think the choice of functions is a really tricky one, and how to kind of pick the right ones there, and how to construct it. I feel like, and this is more of a personal hunch, that there's a strong signal in this kind of presentation of a set, selection of a set, to inform what best to present to the users. So there is, I think, a notion of how you can leverage that information to make it better, if I got your point right. But I feel like it's just kind of opening up the lid for these kind of questions.
Thank you very much.
Very cool. Yeah, so that's going to conclude the session. So let's thank everybody, all the speakers again.